see you here. Welcome to the 21st International Conference Electronics. It is a great pleasure to see you here in Palanga Resort. Some of you have been here before, and as in the Louis Armstrong song, I see friends shaking hands, saying, "How do you do?" We hope it means you find the conference valuable and they stay enjoyable. And we would like to see the others next year as well here. If you know somebody who wanted to come but could not this time, encourage them to watch our live broadcast on the conference on YouTube. We are meeting here in the times of fourth industrial revolution. This is very interesting and challenging time because electronics, robotics, automation, and other fields we are working in are crucial for this revolution, and it depends on our efforts how fast and successful this process will be and which result will be achieved, how it will change the world and the human's life. We know that some people, even very famous, for example, Umberto Eco, who passed away last year, they were quite, like to say, skeptical on whether the technological progress is the really progress for human beings, or even Friedrich Nietzsche joked, I hope joked, the scientist is the God's worst smile. We have to prove that it is not true. Today we will start our conference with two inspiring invited speakers who will speak about the very important topics of ultrasound, and after that researchers from many different countries will present their work. I would like to ask you to be active listeners and express your curiosity freely. After all, debates and discussions are what conferences are really about. The discussions do not need to stop after the sessions. We have prepared an interesting and entertaining evening program where you will have a chance to experience the Lithuanian hospitality. This casual atmosphere is an opportunity to know your colleagues a little better. We try hard to make this event positively memorable, but it is really you who make it worth attending. So, thank you for joining us, and let the conference begin. And I invite my colleague, Darius Andriukaitis, to present some details of our program, especially evening program.
Yes, I think so. So, thank you for General Chair. Okay, so good morning everyone. I'm Darius Andriukaitis, and it is my pleasure duty to welcome you all here today to our conference. And as it has become already a tradition to give some information about conference and about upcoming events. So first of all, I would like to present the map of applicants. And okay, so this year we received submissions from 32 countries from all over the world. And the review process was very strict, and after such strict process. Finally, we have participants from 23 countries. This year, the most popular topic was electrical engineering, and the second one was system engineering and computer technologies, and the third one is telecommunications engineering. Such situation was slightly changed after evaluation, and on the top is telecommunication engineering, as you can see in the program. Talking about our social events, maybe this is not social event, it's obligatory. So lunches we will have in our hotel restaurant, Pelicanas, and the time is from 12:30 to 13:30, all the days at the same time. You should have your tickets for all 3 days. And during coffee break, the waiters will ask you what would you like to eat during lunch. So just don't afraid, they will inquire about this one. Talking about social events, so we will go to coffee house on the beach at the Baltic Sea, and we will have natural fermentation, sparkling wine, and brandy degustation, and so-called evening session, and it lasts up to 10 p.m. We will start from the hotel, and some of us will go with electric vehicle, and some of us will go by on foot, and after that such electric vehicle will come back and take the rest of us. And we will travel from hotel up to coffee house. It's 2.2 kilometers. It is not so far before dinner to walk. Okay. On Tuesday we will have a bus trip and conference dinner. We will go in the middle between two cities. It's between Klaipėda and Palanga. There is a restaurant so-called Gamtos Perlas. And here we have possibility to visit museum of hunted animals, and there is a slight recreation area to walk around, and after that conference dinner will be served here. So here you should have such ticket, because waiters also will collect and based on what you have they will prepare a hot meal. And after conference we will have let's say closing session, and I would like to ask you to participate in all sessions in order to fulfill such form, best presentation, because we have from our partners special award to best in order to give it to best presenter, and based on your opinion we will give such gift during closing session. So just please give us feedback from sessions, okay? What next? Also, we would like to receive feedback from you about our conference, about the whole organization process and how sessions were held, and I would like also to ask you to fill in such evaluation form and put all marks as you imagine they could be, and just put into envelope and back to us, okay, after conference. And thank you, and have a nice conference. Keep your tickets with yourself. And I would like to invite our first invited speaker, Thomas.
Yeah. Perfect.
Okay. So, and video is here, yes.
Yeah. F5 is skipping.
Yes, S5 and
Oh, okay.
and,
Any of that,
and,
yeah.
and yes. Oh,
Nice, okay.
shift it.
And you have
Yes,
this one.
yes, please.
Okay, thank you. Thank you very much. First thing I have to say is that I'm delighted to be here today. This is my second time here in this conference. I enjoyed very much first time and decided to come back here. And I have to say thank you also for the organizers to invite me to give this invited talk, especially to Andrews and all people who make possible for me to be here today, and also to my colleague and friend Linus to host me last week in Kaunas University. I think it was a very interesting stay, at least for me. Okay. Well, this is the title of the presentation. This is my name, and this is where I came from. Spanish National Research Council is a public research institution, and it's a public research institution. It's the largest public research institution in Spain, and we have centers all over Spain, and this particular one is in Madrid. Okay. Okay, an overview of the presentation. As you have seen on the title, the presentation is about ultrasonic transducers operating in Earth. And this is going to be a quite general talk, just to give you an idea of what are the technologies that we can use for this, what are the different applications, and there are a lot of different applications. I am only going to review a few of them because there are a lot of them. I hope you find this talk inspiring for you in order to apply these kind of techniques to whatever problem you may be interested in. So I will talk a little bit about challenges of this technology, opportunities, and then I will describe you the two main transduction technologies available nowadays. They're based on piezoelectric and transducers and capacitive transducers. And concerning piezoelectric transducer, we may have low frequency devices or high frequency devices. And the applications are different, and the way to make the transducer and to produce the technology is different as well. And then we have capacitive transducers, and we have two kinds of capacitive transducers. We have conventional electrostatic transducers. They are more or less like a microphone. And we have these capacitive micro-machined ultrasonic transducers, which is a quite completely different technology. Finally, I will review some of the applications. Okay, let's go. Well, an air-coupled transducer, an air-coupled ultrasonic transducer can be a transmitter and a receiver. And what we want with a transmitter is to convert an electrical signal into an ultrasonic signal and send it efficiently to the air. So we have an electronic system that will generate an electrical signal. We apply this signal to the transducer terminals. What we have within the transducer is that we convert the electrical signal into a mechanical one, and eventually what we want is to radiate this signal into the air. We have three main steps here. The first one is to is the matching between the electronics we use to generate the signal and the transducer. The second critical step is how do we convert the electrical energy into mechanical. And the last one is how do manage to send this mechanical signal that we have in the transducer into the air. And we may want to use an ultrasonic receiver, and an ultrasonic receiver will do the other way around, so it should pick up efficiently an airborne ultrasonic signal and convert it into an electrical one. So we will have, this, in this case, the signal coming from the air. We will transfer this energy from the air into the transducer. We will convert the mechanical oscillation into an electrical one, and finally we apply to the terminals of the receiver, and we detect this with a receiver and a scope, whatever you may want. Okay. What are the main challenges? Well, we have challenges in these three main stages here, but by far the biggest problem is here. We need to be able to get the energy out of the transducer into the air. And the main reason is because of what we call the difference between the acoustic impedance of the transducer and the acoustic impedance of the air. So this is the reflection coefficient and the transmission coefficient at an air-solid interface. So this set is the acoustic impedance. Acoustic impedance is similar to electrical impedance, and the more different are the acoustic impedance of the transducer and the medium, the less energy I am able to get from the transducer. So just for you to have an idea, the acoustic impedance of the air is 410. These units are international system, and the acoustic impedance of any material is in the range of mega rails. So we have 4 orders of magnitude. That means that at any interface between air, for example, and steel, we have 44 dBs. If we are using a PCT ceramic to make the transducer, which is a piezoelectric ceramic, I will talk a little bit about piezoelectric ceramics later on. The loss that we have here is 43 dBs, so this can be very, very large. But there is a second problem, and this is given by what we call the Snell law and refraction. And what happens is that when we go through an interface, we have the ultrasonic signal goes from air to a solid, for example, and because of the difference in the velocity, we have refraction. So that means that very soon we will reach an angle for total reflection, and we cannot enter into the material. So the situation is that if incidence is normal, almost all the energy is reflected back. If incidence is not normal, we have whatever angle, then the energy will go along the surface and you will not penetrate into the material. So it's quite challenging. This is the main problem. Okay, so because of this, we can talk about 2 kinds of applications. In the first one, we will have pure airborne propagation. For example, we have one transducer transmitter and another transducer receiver, and we want to go from transmitter to receiver. In this simple case, if we are using a PCT ceramic, we will have about 80 dBs loss, just for having 2 transducers, not one. Very similar, sorry. Very similar is this case here. Instead of having 2 transducers, I just have 1. This is what we call pulse echo, because we will send a signal and we wait for the echo coming from whatever material we are interested in. But we also can have a combined situation when we have both airborne and solid-borne. And this case is not so bad because it is difficult to get the ultrasonic signal out of the transducer, but once the signal is in the air, it's okay. When you arrive to the material, we don't want to penetrate into the material, we just want to produce a wave that is propagating along the surface. So this can be a surface wave or a lamp wave, and this is not so difficult. The most challenging case is this one, when we want to propagate an ultrasonic wave through a solid material. Probably we want to use this the information of the signal to learn something about the material or whatever. But this is by far the most challenging situation. So, depending on the application, we can be interested in different things. So we may want to have a focus field if we are interested on a good spatial resolution, or maybe we are interested in a diffracted field because we want to have omnidirectional field. We may want to have low frequency or a high frequency, or maybe a short pulse to have a good resolution in the time domain, but also maybe we are interested in a long tone burst. So for different applications, we will use different transducer, and different features require many times different technologies. So, just a few examples. I'll go through some particular application in more detail at the end, but just to have you a global sense of what we are talking about. So this will be the case of through transmission, two transducers. I can use this for ultrasonic airborne communication. And this can be very useful for short range and secure wireless information transfer. In this case, I do need wideband. Otherwise, I cannot transfer information. And I also would need a good signal-to-noise ratio. But this can also be used as ultrasonic beacons. I don't know if you are familiar with that, but there was a strong controversy some time ago because they can be put in Android, as this was the first version that supported to scan beacons, and the beacon can communicate with the phone using ultrasonic signal through the microphone, so you are not aware of this, and well, this raises some security concern some time ago. We can use this also as a source of wireless power transmission. We can use a transducer sending ultrasonic energy and a receiver to use this energy to convert into electrical and charge whatever device. And we can use this for gas flow or air gas velocity measurement using either transit time techniques or Doppler techniques. You can put this on a pipe and you can measure if you have a gas in the pipe, you can measure the velocity. Okay, this will be the pulse echo technique, and we can use two configurations, one single transducer or two. And then we can use this for a quite conventional thing, this distance measurement. All of you probably are aware of this application. It's everywhere almost. But you can also use this for presence detection, for surface profilometry. And this is the last one, and quite interesting, is for non-contact human-machine interface, or what they call gesture recognition. And there are some phones trying to do this, there are some cars. This is quite popular in gaming industry and also in some other parts of consumer electronics. So the advantage of using an ultrasonic technique and not a camera, a time-of-flight camera, or infrared camera, or laser, the main advantage is that this technique is independent of illumination condition, independent of the color or the brightness of the object you want to track. Okay, this will be another one. We use a transducer to generate a surface wave. This wave is traveling through the material and we can detect. This is mainly used in non-destructive testing, NDT, and this is quite convenient because it permits you to avoid contact with the sample, and in some cases this is important because we don't want to introduce any contamination or any alteration of the material. And this also permits fast scanning, and well, this is an example of this using in the railway inspection. It's relatively old, using a combination of laser and air coupler technique, and this is the railway. Okay. This will be another case where you generate a lamp wave on a coating, and this is a lamp wave generation. Two ultrasonic transducer to generate a lamp wave in a plate, and this is an example of a well inspection. You have a well here between two plates, and then you have one transmitter transducer, one receiver, and you propagate the ultrasonic wave through the well so that you can determine what is the integrity of this well. And this is the one that is most challenging, to go through two interfaces because you have to go from the transducer to the air, from the air to the solid, from solid to the air, and finally from the air to the transducer. And losses can be as high as 200 dB. So unless you do something intelligent, you will not be able to do that. And this is an even worse case where you have a sandwich structure. This is quite common in the aeronautical industry. Okay. So this is a transmitter and receiver, and in both cases the key word is efficiently. We need to send the signal to the air efficiently, and we have to do this in the other way around as well. But efficiently means different things for different applications. So let's review this a little bit. We have two main technologies. One is using the piezoelectric effect, and the other one is using capacitive or electrostatic effect. And they are quite different, and they require different equipment, and they are useful for different applications. So, I don't know if you are familiar with that, just a few words about the piezoelectric effect and how we use it. So, if you have a piezoelectric material here and you have two electrodes, the piezoelectric material converts the electric field into a mechanical stress or strain. And in this case, if you apply a stress, and then the material compressed, and it generates an electrical field. If you produce a stress in the other way around, the electrical field will have the opposite sense. And if what you do is you apply an electrical field, and you have a mechanical stress, and the other way around. So the key parts are: this is a microscopic phenomenon, take place at molecular scale. This is linear, and you have both the direct and the converse effects. That means that you can apply an electrical field and get a mechanical deformation, or the other way around. You can apply a mechanical deformation and get an electrical field. So, first piezoelectric materials dates back to the First World War, and they are quartz and Rochelle salt, and they are truly piezoelectric. So, piezoelectricity is produced by a non-symmetrical distribution of charge at the molecular level. So you have a separation between positive and negative charge. This gives rise to a dipole. If you produce a deformation, you deform the dipole, and this produces an electrical field. What we are using nowadays is something completely different. This is the ferroelectric effect. And in the ferroelectric effect, what we have in a few words is that the distribution is not non-symmetrical, as in this case, but we have a displacement, a slight displacement of one of the atoms within the structure. And the key point is that we can make this atom here, this ion here, to jump either up or down depending on the electric field we apply. So that means that we can polarize the material, and we can start with a material that has no response, and after polarizing it, we will have some piezoelectric response. This opened the way to use ceramics. All ceramics are ferroelectric materials, and all materials we are using nowadays are mostly ceramics. We are starting to use single crystal now, but this is a different story. Okay, next step in piezoelectric materials is to produce composite materials. And first composite materials were doing something like this. You start with a piezoelectric material, you cut it in one direction, cut in the other, and then you fill the holes with an epoxy resin. This is quite important for us because this allows us to engineer in the properties of the piezoelectric material so that we can change both bandwidth and impedance. And changing impedance is quite interesting for us because we can improve the matching between the transducer and the air. Okay, this is another configuration that is also available nowadays. Instead of cutting the material, you have fibers embedded in an epoxy resin, and results are very similar. So, if you have a piezoelectric disc like this one, and then you apply the voltage here, and you measure the impedance, electrical impedance, what you have is something like this. You can see that there are a collection of two different vibration modes. These here correspond to the vibration of the ceramic in this direction. Ceramic is doing something like this. And these resonance here correspond to the vibration of the ceramic, something like this. So actually what you have is you have both. The ceramic is vibrating like this, and because of this, it's also vibrating like this. We call this lateral or radial modes, and this is the thickness mode. If you use a composite instead of a bulk ceramic, what you have is you are almost going to kill all vibration in this direction because of the presence of the interfaces. And this is the red curve here, where you kill almost all lateral modes. Well, depending on what you are interested in, this is good or bad. I'll show you. But you can imagine that, well, this dimension is much larger. This is why these resonances linked to this movement are located at a much lower frequency. If we produce a bimorph with a piezoelectric material and a plate, for example, on a metal plate, and we use this vibration in this direction, then what we are going to have is something like this, and this is very efficient to produce radiation into air because the material is going to move something like this. The movement is going to be very large, and this is going to be a very good transducer. But the problem is that this is a low frequency transducer. So this is how we produce low frequency transducer for a couple of applications using a piezoelectric ceramic. But if we are interested in the high frequency regime, we are interested in this one. And in this case, we don't want to have this resonance interfering with these other guys. So in this case, it is better to use a composite so that we can take rid of all these resonances here and have a nice resonance here. So if we are going to work in low frequency, we will use a ceramic in this configuration. If we are going to work in the high frequency limit, we will use this one, and we will use the thickness mode, what we call the thickness mode. Okay. Low frequency devices. Probably you are familiar with this one. It's quite popular. How does it work? Well, this is what I have said you before. You have a piezoelectric disc is here. You have a plate, metal plate here, and only this is enough. But to improve the efficiency, what they do is they put the horn here, and when this vibrates like this, then the horn is doing something like this. And what you have is that the amplitude of the ultrasonic wave that you produce is very, very, very large. So this is quite good. The price that you have to pay for having this high amplitude wave is that this is quite narrow band. This is going to be narrow band and low frequency. This is the impedance, the electrical impedance of this device, and this is used to be about 40 dBs, and this is the whole system. And you have here a lid to protect the transducer, but you need some holes, because if you don't put holes here, the ultrasonic energy is not going to go outside of the transducer. So in some cases this is okay, but in some cases you need a transducer that is able to withstand environmental condition, rain, dirty water, and so on. So these holes are not convenient. Okay, and this is a closed design. This is similar as before, but now the ceramic is attached directly to the lid, and then you have this vibration, and because you don't have the horn that we have before, the sensitivity of this transducer is not so good as the one before, but the advantage that you have now is that this is completely waterproof. So in some cases this is much better. And these devices are normally used for distant measurement, present measurement, and also in some cases for gesture control. And the thickness mode is completely different. You have your piezoelectric material here, the electrodes, and the piezoelectric material is going to vibrate like this. But in this case, we will have a very bad interface between the air and the piezoelectric material. Piezoelectric material used to have a very, very high impedance, which is not good either. What we do is we put some what we call matching layers, and they are normally quarter wavelength matching layers. So you can put several quarter wavelength matching layers just to improve the performance of the transducer. So it is a good exercise at this point to ask yourself, what will be the best transducer that I can build using this thickness mode? So, and without any further consideration, you can start putting matching layers and try to optimize the device. We use a figure of merit. Sorry, is this one the figure of merit? Peak sensitivity and bandwidth, because we want to optimize both, and we start increasing the number of matching layers for a bold ceramic, for a ceramic composite, and for a single crystal composite. And as the number of matching layers, we increase the number of matching layers, the figure of merit increase up to a limit. This limit is 6 matching layers for a ceramic, about somewhere about 7 matching layers for a composite, and maybe 11 matching layers for a single crystal composite. Let's have a look at the behavior of the transducer. Well, it's something amazing. There's almost no loss. We were expecting something about 45, 43 dBs. There's almost no loss, and the bandwidth is huge. We will be very happy with these transducers. And the signal is not bad. Can we make these transducers? And the answer is no, we can't. Unfortunately, at least for a moment. And the reason is that for many of the matching layers that we need to put here, we do not have the material, or we do not have the way to produce them. So, in the end of the day, we only can use some realistic materials, and the best material we can use is a material with an impedance like this one. And in most cases, we have to deal with materials with this impedance, but the problem is that we cannot go so low in the impedance of the material as we would like, because such materials do not exist. And okay, if this is fine, then what happens is that the figure of merit decreases and the number of matching layers we can put decreases. And well, how good is this transducer that we can really make compared with the ideal one? Okay, this is the ideal one, and this is what we really have. And this is something that we can also achieve. Well, we are going from almost 0 dBs loss to 35, and the signal is not so nice as before. This is what theory said, ideal case, realistic case, and this is what we really have. Well, not bad. This is our signal here. We don't have these sharp peaks here because real materials do have a lot of attenuation. Okay, then what we have is an optimization method that we call optimization under non-ideal conditions. And because we don't have the materials that we need to make the ideal transducer, the optimization has to be performed under severe constraints because we don't have this material. So we are doing some kind of optimization, and we can go from this design, this is the one where we will get, to this one. These are real data, where we can optimize the result of the transducer by detuning both in frequency and impedance the matching layers. So this gives us some kind of improvement. And using this technique, we can produce nowadays transducer at 2 MHz, and this is the response, 0.7 MHz, 0.25, and 0.4. We have some others in between, just not to bother you. We have some data in this web page, and all of them are there if you are interested in that. So the key point is that we have a reasonable bandwidth. In this case, it's almost 70%, which for air is amazing. And the loss is quite low. In this case, we have 23 dBs loss. This is even better than many water-coupled transducers that are used for medical applications for water immersion. So having this such good transducer, there are a lot of things that we can do. We can compare. This is the one that we have seen before, with this horn doing something like this, and this is the one that I've shown you here. This is our 250 kilohertz transducer, and even considering that we have no horn doing something like this to move the air in this case, the performance is so similar, and we also have the advantage that the bandwidth here is much larger than in this case. And we have another advantage, is that the frequency is much higher. So this is the signal that we get with this kind of transducers, and this is the signal that you get with this one. So spatial resolution is much more better. Okay. I just tell you a few things about, this is the other technology. In this case, we don't use a piezoelectric transducer. This is a capacitive transducer. So you have a metal backplate with a rough surface, and then a metallic surface, and then you have some kind of isolation in between. In this case, the main difference is that you need a bias voltage to polarize the system, otherwise it doesn't work. When you apply a bias system, what you have here is a condenser, and then you have a capacitor, you have positive and negative charge, and if on top of the bias you apply an RF signal, that you have is this membrane is going to vibrate and is going to produce ultrasonic signal. Well, these are some commercial devices. The main advantage of this technology is that it produces a much wider bandwidth, but the transducer is not so sensitive and the transducer is not so rough as before. And this is the technology for CMOS, which involves microfabrication techniques. So this is quite convenient because you can produce very small transducer and you can integrate electronics. You can put CMOS electronics integrated on that, and this can be very, very convenient. So a few words about applications, and we can go as far as we have time. This is one of the first one. This is quite conventional. It's a surface profilometry. You can do two things. You can do time of flight, and then you know what is the distance between the transducer and object, but you can also measure amplitude. In the case you lose amplitude, you know that there is something like this in there. This is one of the first results from Schindel, 88. This is the ultrasonic image of a coin, of a penny, and this is using time of flight, and this is echo amplitude. This is an application we developed sometime later. This is to produce a scanner for Braille text. This is the Braille written here. This is this writing for the blind, you know, where you have some dots. And the dots are somewhere here, because you have different colors, you cannot see them very well. But if you make a scanner for this using a focused ultrasonic transducer, what you have is you have a lot of energy when the surface is flat, and a lot of energy on the top of the dot. But when you are on the side, you lose energy, and this is what you see. As far as I remember, this is an O, this is an S, this is a, well, this is a very old application and a very new development. This is for level measurement in a test tube, and ultrasonic techniques have been used. This kind of ultrasonic technique can be used for level measurement for ages. But what is new here is that we have a very small enclosed. This is for a test tube, and the idea was to make a very small transducer to be able to put it on the aperture of the tube and integrate the whole thing. So integrate battery and integrate the electronics and integrate an antenna, so that we can integrate the sensor in the Internet of Things. Okay, this is a quite interesting one. I will talk about this a little bit later today. So basically what you do is that you have a sensor, and the sensor is able to recognize what you are doing, or if you are moving your hand or whatever you are doing. And you have different technologies for that, but one of them that is quite interesting is the use of ultrasonic signal for this. And this is the last one, which is to integrate this non-contact human-machine system in a car. This is from PSA group, but in this case they are not using ultrasonic technologies. Ultrasonic waves are being used with smartphones. They try to use your microphone and speaker to produce ultrasonic wave and try to interact with you, so that if you say something like this, the phone understands or whatever. And I would like to go to the most difficult one. This is NDT, and through transmission. So in this case, you remember we want to go through the material. So this is a quite challenging one, because well, we want to detect defects. They are quite small. We may have different interfaces. Surface can be non-planar, so you know when the surface is curved, all the energy is going to go away along the surface. And the impedance of the material we want to expect can be very large, so the reflection is going to be very large. And so in this case, we need extremely high sensitivity transducer, and we need wideband response, extremely good signal to noise ratio, and a very good matching with the system. So I'd like to show you a video, if it works. Hopefully. Because this is sometimes this is difficult to believe, so better show a video. you can do it better. We have the couple of couplet transducer with transmitter and receiver, or the other way around, I don't know. And this is a pulsar, and this is the signal that you have in the scope. This transducer are 250 kilohertz transducer, and they are focused. And when you put something in between, this is a thick graphite block, and the signal completely disappears. This is because of the reflection. You increase 10, 20, 30 dBs, 40 dBs, and then you have the signal here. We are transmitting a tiny ultrasonic signal that is vibrating through the material. You have a nice signal here. You can see that the signal distorts very much because the multiple reverberation within the material. Okay, but this is easy because the impedance of this material is not that big, the attenuation on this material is not that high, and well, that's something different because it's a sandwich structure. We have 1, 2, and 3, and 4 different interfaces. The attenuation in the honeycomb, this is a honeycomb, aluminum honeycomb is going to be extremely large, and you can see that the signal almost disappeared. We can try to increase average in here and to increase the voltage in the pulsar or whatever, but the best idea is to improve the matching between the transducer and the electronics. So we reduce the gain here, and then we insert the preamplifier, and this preamplifier is giving us some extra gain, but the main thing it's giving us is a better coupling, electrical coupling between the transducer and the system. And then we put the sample again, and okay, here we go. It's a nice signal. And this material is extremely interesting for NDT in the aeronautical industry. Most of the components, lightweight components, are made with this kind of material. And the most amazing one is this one. It's steel block, not flat surface, very rough, very dirty, very everything. So the impedance of this material is extremely high. So we have about 90 dB loss in the transmission. And here we are. It's a nice signal, and this can be used for. This is still another example that's really. Okay, this is the transducer mounted on a QCAR robot for a real testing on the real world in the industrial environment. And this is a real result of this kind of thing with some defects to be put in between. And well, this is another example of the implementation of this technique at the industrial level. And okay, I think we are on time. This is one very interesting thing is you can use this to measure the mechanical properties of very soft materials. So in some cases you are interested in mechanical properties of very soft material like scaffolds for human tissue or very light materials. And these materials, because they are so soft, you cannot put them in a mechanical test machine. So air coupled technique can be very good because the ultrasonic way will give you information about the mechanical properties. And this is our top strange application. This you can use air coupled ultrasonic waves to precise watering control in binders, and this is good to improve wine quality and to reduce wine jar diseases and to optimize the consumption of water. I think we all are interested in wine quality. So just tell me the trick. And the trick is that if you transmit an ultrasonic signal through a wine leaf, you can produce a thickness resonance of the leaf, so you can make the leaf to do something like this. And if you register the spectrum and you analyze the spectrum, you can obtain information about the leaf thickness, density, elastical modulus, and these parameters are closely related with the water content. So the magic happens, and then you can determine in a completely non-invasive, non-destructive, and very fast, and the equipment is very simple way, the amount of water that you have on the plant, and you can decide if you put some extra water or not. And okay, just for wrapping up, I've tried to summarize the main technologies for air coupled transducer, depending on frequency, sensitivity, bandwidth, and field geometry, and I've tried to outline a few applications. I've tried to select the most diverse or strange ones, so yes, you have a general feeling of what we are talking about. But there are a lot of applications in consumer electronics, gaming industry, NDT, material characterization, agriculture, food industry, art conservation, distance measurement, wireless communication, energy transfer, and so on and so on. So, okay. Thank you.
Okay, thank you. Any questions?
Actually, Thomas, you have missed MFITs, so what you consider then as piezoelectrical?
No, I don't. There's a new material, which is a polymer, which is charged, and it behaves as a piezoelectric material, but this is not truly piezoelectric. It's something in between piezoelectric and electrostatic. And there are some new advances on making transducer with this kind of material. I consider putting them here because you know we are working on them as well, but I prefer to focus on technologies that are already working and are already completely established, but I wouldn't say they are piezoelectric.
Okay. Any questions? Okay.
Is it these transducers are sensitive to environment conditions, temperature, or pressure, or some other hazard issues?
Well, they work. They don't behave well with high temperature. Okay, I think they work well up to 100 degrees, which is not bad. Mainly for this application because in industrial environment you don't have such high temperature, and you may have problems with moisture content. In some cases, we are able to design transducers that are completely waterproof, but in some other cases we cannot. So it would depend on the frequency, on the transducer design, but moisture can be a problem. Yeah.
Okay, and I have some questions. Do you know if such system with sleeve for pioneers is installed or no, or just it is under research?
Well, we made a basic research to produce all components, and then we have an applied research contract for 3 years to test this in a winery in Spain called Cariñena. I don't know if you are familiar with Cariñena, it's a good wine. And it went okay, and now we are thinking how to go further in this. If go directly in the direction of to produce an equipment for end user, or the other possibility is to produce an equipment for research, because people in researching this kind of things also interested in that. So we'll see what happens.
Okay, so after 5 years we can just degustate results, yes?
I hope so. I would like to do the final testing. So
Okay.
this is the wine test produced without this, and this is the wine produced with this. Which one is better? I would like to.
During conference.
It will
Okay.
be destructive testing. Destructive.
Yes, for sure.
Okay, so thank you.
Okay, we have a small gift
For testing.
Thank you very much for your presentation.
Thank you very much.
Okay, and it's time to have a coffee break. Okay.
Let's start our next session. Also, we have one invited speaker. His topic also related with ultrasound. And Liudas Mažeika, he is director of Ultrasound Institute, and will present topic ultrasonic measurements, trends, problems, and solutions.
Hello everybody. Welcome you to gather there in Palanga, very nice Lithuanian city near the sea, and I hope there will be very good atmosphere, scientific atmosphere inside conference, and good weather outside, maybe with rain a little bit. But so my speak will be a little bit different. I will come from some basic of ultrasound and then illustrate with some different examples of my experience. And I am from Ultrasound Institute in Kaunas University of Technology, and this is not new. I will say very old institute concerning ultrasound, because it's established maybe 55 years ago. So as for ultrasonic field, it's very old. It's because ultrasound in general is probably first applications I will mention appears in somewhere in Second War for location of submarines and so on. So the first, what is ultrasound? It's me talking without this. Yes, and ultrasound officially say that is acoustic waves higher than 20 kilohertz. In general, it's very relative, because people can hear, some people hear, especially young, a little bit higher. All the people hear a little lower. But it's like to say official definition of ultrasonic waves. And however, they goes very high. Now there is such technique as acoustic microscopy, which goes probably up to even 1 gigahertz. It's acoustic ultrasonic waves, but it's very special application. And of course, this is pressure waves in gases and liquids, and elastic waves in solid materials. So, but not humans invented ultrasound. It already existed in nature. It's one of animals which use it is dolphins, which have communication, and probably they locate the target or some obstacles. And another one is bats. Is also they used widely. They can fly in the darkness and just to locate all situation with ultrasound. And I will say that these two equipments probably in some sense much have advanced than we have now ultrasonic equipments. In some sense, we have of course developed very different instruments which, like to say, goes further from them. But in some sense, they are very innovative. And the first application of ultrasound in humans is probably started from detection of submarines and ships from submarines, depth of the seas and lakes. And so this is first application. And the advantage of ultrasound is that can penetrate through not transparent for light materials. It's like to say key advantage of ultrasonic waves. And if we look where it's very briefly where it's widely used, it's two areas. I think for public probably one is more known, is medicine. I think women probably all know about that, or at least they will know in future. But anyway, but it's not detection of babies, but it's heard and it's very widely used in medicine diagnostics. And another area is industry, and there's a little bit very different objects. In medicine, there is very concentration because all we are the same for ultrasound, more or less. It's not exactly. For example, blood, ultrasonic properties of blood, women's and men's are slightly different, but very little. But in general, for ultrasound, something very close to water. except of course bones, which are some composite material, like to say. It's a completely different situation in industry, because there's a plenty of materials. It's metals, plastics, even metals, they are very different. For example, conventional steel is very transparent, but the so-called stainless steels, austenitic steels, which can have very, very big grains, and in this case, they are very attenuating or scattering. So also it's composite materials, it's some viscose materials. So in industry there's plenty, much wider area, much wider space for materials, and because of that, it's much more different instruments. In medicine, they are concentrated for imaging and for some measurements in biology. In industry, it's very, very, very widely. So the next question is why it's necessary to look into these metals. Why to look in our body? We know. We want to be healthy, not to have sickness or so on. But why we look? And one of the widest field of ultrasonic application is detection of defects, different defects. And this is, like to say, very well-known examples of accidents. There are plenty of them. And in all cases, they are checking for defects, but not always succeeding. So this is an accident of Intercity Express train in Germany. It's at 200 kilometers per hour, he crashed. And the reason was defect in the wheel, just defect, small one, which lead, of course there's some other conditions we have been, but anyway, primarily is defect. Another is ultrasound. We have some accident in our oil refinery, very close to there, I don't know, 50, 60 kilometers somewhere, 70 maybe kilometers away. And it was a big fire, and the problem was also some corrosion, not checked before. So not to check usually costs very big money for industry. And another one is accident, is maybe very successful accident. Nobody have been damaged. It's in Kaunas. The bridge was dropped down a little bit, not completely, but a little bit, because there's some steel holders which just crashed. And why crashed? Not badly calculated, but just appears some defect which is developing. Another feature why is inspected nuclear power plants, pressure vessels, different things, that all defects are keen to develop, to grow, because cracks is very narrow. At this very end, they have some concentration of tension, grows, and fails. So now it's. I mainly will talk about industrial applications, not about medicine, because about medicine, even in this case, I can talk for many hours, for up to the Wednesday, but maybe not this time. So it's just example that there is some transducers which propagate ultrasound inside, and if they're defect, you get detecting some non-uniformity, and you can estimate and so on. So it's possible to detect some non-uniformities, defects, to measure properties, and I will say that it's only method which directly related to elastic properties. Elastic properties is strength, density, different things. So it's only method. There's other methods can be used. Sometimes electromagnetic, I don't know, some independent measurements, but method, because properties of ultrasonic waves directly depend on material elastic properties. So there's a changes in material properties, there's change in our signals. So, and another thing, advantage, that this is it is non-destructive method. It's not necessary to cut. I do not speak about medicine, but it's in industry, it's not need to cut piece, to take piece, to measure, is it strength, is it defect, to look inside. So, on the other hand, ultrasonic measurements looks very simple. We have already previous presentation that you have transmitter, receiver, one side or reflected to the same side, and just measure signals And from these signals, it's necessary to measure, for example, time of light, attenuation or scattering, sound velocity, structural noise, for example, is related with scattering, propagation direction, and from these values you can estimate, I don't know, properties of material, even of liquids, if there are some changes in content of materials. Probably you all already used, for example, you know, thunderstorms and lightning, yes? How far they are? Usually people say that, okay, you see lightning and then calculate 1, 2, 3, 4, 5, and then divided by 3 up to the thunderstorm. And the distance is to the, you're getting the distance in kilometers. Why? Because ultrasound velocity in air is about 340 meters per second. So 1 kilometer is passed around 3 seconds. So we can easily, ultrasonic measurements, sonic measurements, but the same. Just question about accuracy. And from these parameters, you're getting elastic properties, viscosity, dimensions of the object. For example, you're getting echo, you're getting distance, density of material, non-uniformities. For example, you're detecting that in some place ultrasound velocity is a little bit different from another. What does it mean? It means that there is some difference in some properties. Why? It's not ultrasonic question. Usually there is some structure integrity people which determines what can happen there. Temperature, pressure, and so on. So just advantages and field of application very briefly. So first one is enables to look inside the objects. The second one is very important, non-dangerous. For example, even for humans, both ultrasound and X-rays are used, but usually do not enable to use X-rays, photos, or tomography very frequently, because X-rays are dangerous. Especially in industry, in order to get image, like to say X-ray image of some metal plate or object, energy used is much more higher. In this case, in general, is dangerous even for life. So yes, X-rays also used to look into the non-transparent materials, but it's very restricted where it can be used. So it's problems with safety. Also, it enables online measurement. You can put some instrument, and even you can put transducers inside the object and to monitor what happens during, I don't know, exploitation or just performance of some. And also it's that it's possible to investigate in micro and micro scale. I mean, macro, for example, what ultrasonic ear couplet through ear usually have lower frequencies, 40 kilohertz to 200 kilohertz, but it's related to wavelengths. So if we detect something, it will be at the range of wavelengths corresponding and longer, bigger object. On the other hand, for example, in our institute, we have acoustic microscope, which works up to 230 megahertz. And in this case, wavelengths of ultrasonic waves is in the range of 6 micrometers. So in general, you can scan to look into the electronic chip to determine what is inside. Is it not, like we say, cracked or something like that? And resolution is extremely high. Also, there is a field application. It's non-destructive testing and monitoring due to safety, ecology, and even due to finances. Assessment of material properties, medicine, diagnostic imaging, process monitoring. Process monitoring, for example, measurement of manufacturing of plastics, flow measurements, even, for example, heat energy measurements. There's ultrasonic meters which measure how many energy you're using for heating of your house. It's commercially available instruments. So, on the other hand, I said that ultrasonic measurements are looks very simple, but inside it contains very many sciences, and it's physics, it's mathematics, it's electronics, it's no way without it, and it's informatics, especially in last year, because you're getting signals, what to do with them. It's not electronic operate with them, it's informatics. And I like to say in middle, like to say measurements, because usually you need to assess what you are measuring, not just to get some value. And also there's very important two things, is modeling and signal processing. Modeling is because it's impossible to understand what happens inside structure without modeling. So if to look at the ultrasonic measurements, like to say in more complicated way, so usually we can have many transmitters, not single one, and many receivers, and some medium, which is space. It means x, y, z, and time for like to say for unknowns. And this is very important, because when we excite transducer, we excite by electrical signal, which is in principle just function of time. So the ultrasound propagates in space, and then we're receiving and gave back to the one variable, like we say. So it's very complicated transformation, and it affects in different wave measurement results. And so its medium is at first is 3D pressure wave or 3D longitudinal axial waves in solids. It can be, if we talk about guided waves, what propagates in plates, in bars, in pipes. There's so-called guided waves, and there's not just longitudinal or shear waves. It's combination of them, and it's so-called multimodal media. It propagates very different modes. And diffraction, refraction, attenuation, scattering, dispersion is also dispersion. If we have guided waves, the velocity of them depends on frequency. If we talk about longitudinal shear waves, it's no dependency, almost. It's just the same. It's for metals, for plastics even, there's some dependency, but it depends how accurately measuring. But for guided waves, it's very strong dependence for each mode. And also some things like complex object geometry, extreme conditions, and other things. They affect our signals, and it's necessary to decide what to do with them. So if we look at the very easy at four main parts of ultrasonic, any ultrasonic system, air couplet, medicine, or industry. It's electronic, ultrasonic transducers, scanner, mechanical scanner maybe, and software. Which so if last tendencies, if we look what happens in the world in the field of electronics for ultrasound, so what we say that one thing is essential reduction in dimensions of it. It becomes smaller and smaller. Number of channels, it means that you can connect, I will say later, many transducers or phase arrays, so-called. Integrated units, it means that you can integrate somewhere into the instrument in technology, very small, which performs measurements. And for example, battery powered, for example, if I remember correctly, flow measurement instrument, it doesn't require power supply from the set, but it just works for 5 years or something like that. On batteries, you no need to change. And it's electronics in general. And also price reducing, but to the limits. Because in most cases, it's not like to say for white peoples, but for industry, for energy institutions. So it's still not very, very cheap in medicine, including medicine. Cheapest maybe there's a distance measurements, ultrasonic is tens of euros probably. There's sonars for fishing bands, which look how much fish behind surface. So there are some hundreds of euros, but in general, its instruments are not very cheap. It's just like to say one of examples is company Lecure Electronic announced that they have ultrasonic 2-channel system, which looks like a stick, memory stick. That's all. This is all complete system. Of course, if we go into detail, probably the gain not very big, a little bit noisy, different things. So it's not the case that okay, we have small system and bigger system do not require it. Also, we have usually big tendency to put all menu on the laptop, not laptop, but on phone or tablet. But there is also, I will say, doubt. We have project. I will show later. It's an example of that. But the tablets are not powerful enough for signal processing. So there's still problems to make, like to say, your experiment carrying out and just look everywhere. Not so easy. Now another instrument is from M2M system. By the way, it was developed under one project which we participate together. We're not worked on this instrument, but anyway, but it's just example. It's not say that it's only one company. There's many companies, but it's again all incorporated. It's very friendly. It's very forced to use operator all necessary steps. And one of the version was submergible, or you can put it into water and to work without like to say afraiding that it will be broken, something like that. Now ultrasonic transducers, and if to look what is again tendencies. The first one is that there is a phase array. Phase array, it means we have not single element, but we have many elements, and by exciting them with corresponding delay, we can focus at different distances. In general, there's an image, but we can steer beam in different things. It's very widely used in medicine. It's used in industry also, but with industry problems that you cannot usually scan only one place. You have some weld, some pipe, and anyway, even with phase array, you need to go further to scan object to look. It's not enough for medicine. It's mostly case. It's just electronic phase array, and doctor has mechanical scanner, which looks so it's like this. Another field is ear couplet, because not all materials you can be vetted. Vetted because what in previous presentation you understand that is very big losses in ear couplets. So if possible to avoid the use, but it's not convenient. So for ear couplet there is a very huge attempts from various companies to use lasers for excitation and for reception. And there's such systems exist, but price very big, one thing. Another, they are very sensitive to surface conditions. So on some materials, okay, but if you can imagine industry have some a little bit dirty or some roughness and so on, so it doesn't work. Another, there is integrated with very thin, which you can incorporate into a material. And environment resistance is, okay, just some limitation of phase array. It's two limitations. If to go down, it's very complicated to make many elements. If to go up into the frequency, also limitations. So if we talk about, for example, microscopy, acoustic microscopy, there's no such phase arrays till now. And now about a little environment. This is our development. Is ultrasonic transducer, which can operate at temperatures up to 450 degrees Celsius, can be submerged in liquid lead bismuth alloy. In general, they were developed for operation into the new types of reactors which are cooled by lead bismuth alloy. So additionally, there's a strong radiation, and there was big problem not only to survive. At the beginning, when we have developing, it was seemed that okay, piezoelectricity, all effects die. Curie point is where piezo effect is like disseminated, but there's other problems such as coupling. For example, if you transferring this ultrasonic wave into lead bismuth alloy, so if it is coupling well, it starts to eat even metal, because it's chemically aggressive, very aggressive. So it's just one of examples. And this is, by the way, measured temperature in this alloy using these transducers in our laboratory. Another application is ultrasonic transducers, which used for online monitoring of liquid. Where a problem arises, it's, for example, you manufacturing plastics, and now it's using recycled plastics. And the recycled, a little polluted, it's not very pure, so you need to monitor density, viscosity, otherwise your product will be not qualified, like to say. Now, as I said, it's very complicated to avoid mechanical scanner, but it's probably a completely another topic, because it's very, very wide. For each object you need for some another scanner, because geometry, object, what to put, and so on. So this is very interesting example from Inete company from Croatia. We have project with them together, and this is a robot which can go into the pipe and travel around and to inspect the pipe from inside. So it's like to say, you see like worms some. And of course, in sense of scanners, tendency is to develop autonomous. The dream, again, if you, for example, have some object, you have some welded plates or something you want to test, the dream is to put scanner and go for coffee. Scanner moving by itself. But it's, till now, it's too complicated. There are some companies which start to make, but usually they are controlled by humans, not autonomous. Now software, there's plenty of companies which use and develop different software for modeling in ultrasonic field and for data analysis and presentation. One of them is so-called Extender, which you have developed some so-called Shiba, big like to say software, which big code, which can be used for different non-destructive testing areas, including nuclear, and is certified, and you can get with them different images of ultrasonic signals. You can filter, you can put different transducers, parameters, geometries, and so on. It's very widely used. However, it's not always is possible to use this. If you're getting new techniques, new measurement techniques, or you're getting new materials, it doesn't cover. So just brief need of modeling and signal processing. It's the first one is, of course, ultrasound is invisible, and it's necessary to understand how it propagates, and you want to see, so you need modeling, and to determine irregularities, and afterwards with experiments. And problems to develop methods, because it's very, like to say, models are analytical and numerical. Analytical is, like to say, for some very, very limited cases. Numerical, very good, but you're getting very many sampling points. Well, let's assume very easy task. It's you want to scan 3D area, just 100 is cubic. It's 10�6, and if you in each case have signal, it's gigabytes of information. It's crazy. So the same for modeling and both for signal processing. So it's key issue to get model which is capable to solve this task under the limited resources of computers. It sounds very crazy, but because computer resources grows very fast, but anyway, wishes also goes very fast. This is a very, very easy example. It's modeling of, for example, of ultrasonic field of bipolar transducer. When transducer is created using not one element, but two elements, so with opposite polarity. And also there are some wave propagation in pipes because you're getting very many reflections. So it's just example, very easy examples to what is necessary to develop in some cases. Another much more complicated, related to complex geometry of objects. It was developed ultrasonic system, but there you see a transducer or set of transducer who looks in very complicated object. In general, this is mirror reactor interior. It's a real image, and then you can possible to scan any you want. It's our developments. You can scan in any curves in any positions with any number of transducers, and to get image of the object, what is will be you can expect in reality will be. And without such models, impossible, for example, to develop technique which should operate in liquid lead bismuth alloy, because experiment is too costly. Another thing that, for example, is quite easy, but is so-called nozzle. Is junction of two pipes. Sounds very simple, but in general, it's junction of two cylinders. And geometry 3D is very complicated. And as you know, there is a Snell's law, and when you put a transducer to determine where it's looking, becomes very complicated. By the way, just but now we have very small contract developing simple calculations to estimate where transducer should position in order to look in correct way. Now some brief signal about signal processing. Usually we're getting signal, and in principle it's looks very simple. We have excitation signal, we have transfer function of medium, and we're getting the signal. But usually the task to determine this, not to use, but to determine in signal processing. So in general, we want to extract how medium transfers our signal, and this is inverse task. So in direct way, it's impossible to solve. So many things necessary to do to overcome this. It's just some example of experiments. How propagate ultrasonic waves in plate. Another instrument what can be achieved with signal processing. For example, you know very big storage tanks, yes? And due to ecological reasons, they need to be tested. And the walls, it's easy to test. You can come and check, is it not corroded? But how to check bottom? Bottom, you need to take off all content of it, I don't know, oil, some gasoline or something like that, and to clear, to come in, and it's dangerous, and then to inspect it, and it's done. But the price of inspection, of checking for defects, is maybe 10% from total price, because to clean, to everything, to empty it, is much more costly than inspection in itself. So there was a technique which developed also by propagating ultrasonic guided wave through tank floor from all sides in many directions. You're acquiring many signals, and afterwards you're getting some image where red zones are related to higher attenuation, and high attenuation is related to corrosion. So in general, you can reconstruct the condition of tank floor without going inside. Another very interesting also project is just ended. I don't know, is that there's just the detectors of fire, but there's a fire sprinkler system. It means that there probably, maybe, I don't know, but should be pipes with water, which prepared, if there's fire, they start to put water or gases, I would say. So these pipes should be tested time to time, not each day, but 10 years, 5 years, because if it is not proper way, it cannot work, or it can be even leakage on the computer, on, I don't know, on some other goods in shops or so on. So it's necessary to test, to check it. Is it pipes are correct? So this is my colleagues from project. There's a sample 6-meter pipe just to check for developed techniques to detect defects. They're drilling some hole, you see there, and there is an image of this is angles, but in general it's 16 signals measured. And if you look, the signals look crazy. If to look like to say, assume that the defect should be somewhere in this. This signal was in front of this hole. Nothing. You have some crazy. Another thing that if we look, is guided wave, if pipes. You're getting not like in beginning of my presentation, oh, I'm getting echo, it's very clear. You're getting many echoes from one end to another end and so on. If you zoom this area, the true signal from this hole, but this one. And this is at least 30, 40 dB from the, comparing to the, 40 dB, it's 100th of time, yes. And so it's very tiny signals, how to operate them. Of course, there's a complex algorithm which filters, selects many things, and after that we're getting very precise position of this hole and from distance. And additionally, at relatively low frequencies, it's not high frequency for small defects, but this is somewhere about 50, 40 kilohertz. And not only one, and what tomographic reconstruction enables to determine even distributed. We drilled not single, but many. So technique, what can be obtained with only signal processing, because technique itself, it's used already. It's me. It's also interesting, the instrument, the technique was tested in Cambridge Library, in archives. So it's a very, very interesting place, by the way. Amazing how many literatures you can find from history. It's very amazing. Another thing is, for example, now it's tendency to change steel pipes into the plastic. They are more long-term, can be longer exploited, and they do not corroding inside and so on. And for heating pipes, I think in Kaunas now, very many places they are digging, changing, and these plates, these pipes are joined. There's several techniques, but most widely used is some called coupler with wires, and it's heated and just melted to the pipe. So it's a technique sounds very easy. But you can imagine that it's not like to say you're making factory and after that checking. It's in trench. You're adding another pipe, checking, and you should put the ground on. You cannot wait for some days. And in this case, the people which check should be somewhere there. So they need to check very fast. And it was topic from another project. And the problem is that if you check just on one line, you're getting image like this. This is heating wires after that, and this is correct weld, because if it is bad, you should see there some reflections. It's not welded. But when you're checking all pipe, you're getting about 700, 2000, depending on diameter, ultrasonic image. So if you sit and just check everything, it will goes time running. The people are there just smoking, eating, and doing nothing. So it's not efficient. And so it was developed technique, automatic, just analysis of signals and data, which enables to reconstruct. This is, of course, from sample. Green lines, it detects even heating wires and separates them. Then it detects delaminations, and afterwards it makes some map, like to say, which shows where is defect in automatic wave without influence of operator, just push a button. Of course, not in always. It's like to say we say that we need traffic lights: green, yellow, and red. Red bad, yellow, green good, yellow call man. Which can explain. And the last one may be some interesting also in signal processing. There was problem with so-called creep damage. If steel pipes are exposed in power plants, it was not in nuclear but in conventional, cool heated power plant. If steel exposed to the high pressure and temperature, it starts to a little to creep. And these defects starts to appear from I don't know, micro scale, micro cavities, then they join the micro cracks, and of course grows and breaks. And even we ask in power plant, okay, but it's conventional power plant, okay, pipe breaks, you stopping, repairing, and so why to check before very early and to know? Answer very easy. How long they will stop and start again? 2 weeks. Each week, 300,000 pounds. So it was in UK. So calculating, yes, more, better to check before. So it's just an example, one sample, but maybe, and then you detect in plenty of cracks. I will show a little later. But again, I previously showed very little signals. You see in this image, it's original signals measured in our laboratory on test sample. You see this is surface reflection and nothing. After smoothing, compensation of the mismatch of axis, removing of top surface reflection, we can see some sign patterns in general which indicate that there are some reflectors inside which moves when we rotate according tomographic reconstruction. So if we just analyze this area, we're getting image like this, where it's possible very easy to see that this is parent metal, one structure. This is a more noisy in sense of ultrasonic signal. It's weld material, and inside there's some so-called heat effector zone, which is more fine grain have and more smaller structural noise. If we look at these red dots and start to reconstruct tomographic reconstruction of this, we see very precisely indications, which is not like to say very clear, and even you can get position. By the way, we check this also with tomographic X-ray, with X-ray tomography, and failed. Failed is because X-ray depends on density. Density of steel quite high. So higher density, the less resolution. These reflectors or some non-uniformities are very tiny. It's maybe I expect that it's some tens of micrometers, maybe cavities. So it's impossible to obtain sufficient resolution. And afterwards, from this, it's possible to create 3D image. And it was, by the way, this is noise where we suspected that is already damaged by creep. And this is metallographic analysis of the same sample. You see that as fitting, there's a small cracks, and I will zoom one. If we zoom this area, we're getting like this, and you can see this distance is 200 micrometers. So you detecting quite tiny things using, in principle, just signal processing. Thank you. Questions?
Please ask your questions. We have
Several minutes.
maybe a few minutes. Some questions?
Too clear.
Okay, then thank
Okay,
you. It's
thank
time
you.
for lunch because the
Thank you.
maybe it's not that reservation. start our session of electronics. And the time limit for each presentation is 15 minutes total time. So please fit in time, maybe 12 or 13 minutes for presentation and 3 minutes for questions, okay? And we have first presenter from Poland. I think he present himself, and the topic is temperature influence analysis on the selected current sources stability in the static and dynamic operating state.
Can we start?
Yes.
Okay, thank you. My name is Wojciech Walendziuk. It's quite not so easy to pronounce name and surname. So I will talk a few words about analysis of temperature on current sources. So my presentation, firstly, I will start with some introduction, then I will say a few words about tested current sources. Oops, sorry. Next, I will say about something about the laboratory stand and research procedure and achieved results. So the goal of our research was to analyze the temperature influence on current sources. We have chosen only 4 types of well-known circuits. The first test consisted in changing temperature versus load, changing of load for current sources. The other test was related in transient state analysis and during switching on and off current sources to the circuit. I think everyone knows different circuits which can be used for resistance measurement. You can see here, for example, well-known Weston bridge. We can also measure resistance with the use of direct measurement with the use of current sources built in meters. We are measuring in such cases voltage drop of the resistance. We can use Anderson loop. We have here a simplified version without subtractors of this kind of measuring circuit, and we in general working on a different kind of signal conditioner, which name is two current source bridge. We have here 2 current sources built in the bridge, and thanks to that circuit we can measure 2 quantities at the same time. Of course we have to do some calculation. Here we have an example of 2 current bridge in which we have applied 2 current sources which should have identical parameters of electrical parameters. The temperature stability of this current sources is also crucial when we want to apply such kind of bridge in industrial applications. Of course, the circuit can work when the current sources are not equal, but the formulas for calculating these values of resistance, for example in strain gauge system, or with the use, for example, temperature sensors such as platinum sensors, these formulas are more complicated in order to express its values. Next next version of our current source, double current source bridge is a bridge with some keys built in the system. In this system, the source current source properties are important if we take into consideration dynamic processes such as switching on and off current source to the bridge. The slower, for example, response, the slower time of the response of the source settling time the smallest frequency of switching this in this bridge keys can be applied. Taking into consideration presented current sources limitation, if we take into consideration static and dynamic processes, we took a decision of doing some research in which we analyzed thermal properties of in a dynamic and a static states. In the research we used 4 well-known devices, maybe not exactly devices, such as by structures of the current sources. First was a well-known LM317 element. The next was linear technology current source. Third was and fourth was a MOSFET transistor-based current sources. Laboratory stand. In this slide we can see printed circuit board of on which we placed several current sources. For, as I told you before, for purpose of this research, we used only 4 of current sources. Laboratory stand. We have used climatic chamber as an environment for our device. Also, we used thanks to this chamber, we can we had a possibility to steer the temperature inside and humidity. What is more, we use programmable electronic load and 2 multimeters, 6.5 digit multimeters. All of devices was connected to the PC computer, which and all of the process was steered with the use of LabVIEW system. The first research was the temperature distribution analysis. As you see in this research, we achieved almost regular distribution of the temperature. This means that there are not additional thermal factors which could be a source of error in our research. As you see, we have some spots. It's lighting emitting diodes, but this part of the circuit does not significantly affect the research results. Here we have an example of a dialog window of our virtual instrument, which was written in a LabVIEW language, G language. Thanks to that, we have a possibility to collect our data during research. In this slide, we can see simplified version of our state machine, which was used in our research, in our program. In the first thread, we steered climatic chamber. Also, we have measured some temperature inside. What is more, the second thread was responsible for sending command to the resistance load, and the third was responsible for reading data from the multimeters. Research results. Maybe firstly about some procedure of measurement. We have chosen the temperatures range between -5 degrees Celsius to 70 degrees Celsius with a step of 5 degrees of Celsius for measurement this source. the temperature, when the temperature was stabilized, we achieved, for example, 5 measurements for 1 point for the characteristic. After that, we can have a possibility to calculate uncertainties of type A and B, and of course combined uncertainties for measurement at that point. After that, we increased the values of resistance load of 5 ohms up to 400 ohms, and so on and so on. What we can see, there is not big influence of the temperature on the stabilized current for current sources. For all analyzed circuits, we will see after. Maybe I will change the current source. In order to see more precisely values of the measurements, we apply differences between specified temperature which was related to the 0 degrees characteristic. As you see here, there are small points, like here. It's a source of error which takes from the resistance load. Yes, it's a kind of, it's a place when here and here, for example, when the resistance load changed the range inside, the circuit, inside the resistance load. It's not so good. What is more, maybe it's information for you how many we have to accomplish measurements during one measurement process. We have to do 3,070 measurements during whole measurement process for one series of characteristics for one current source. Here we can see the characteristics of difference between in relation to the 0 degree. As you see, the differences are not big, and in the stabilized part of the characteristic, it's a source of errors I have told you before. This part of characteristic is not important in a practical application. That is why we can. It's not necessary to take it into consideration. Okay, for linear technology, it's adjustable current source, and for MOSFET transistors, as you see, errors are bigger than in previous types of current sources. Second test we did during switching on and off current source to the measurement circuit. The test was accomplished in the temperatures of -5 degrees of Celsius and for 70 degrees of Celsius. The load resistance was 100 ohms, and we switched on and off 10 times current source during one research. Okay. As you see here, the smallest difference between rising and falling time occur for MOSFET N-type transistor, but huge settling time values around 1 second and rising time about 0.5 seconds are disadvantage of this current source. For our application, linear technology current source was the best choice. if we take into consideration smallest, of course, and rising and falling times, and what is more, settling time for different temperatures. Okay, summarized. The current sources, based on the integrated current sources, was the best solution, optimal solution in our application. If we take into consideration dynamic states and, of course, static states, and what is more, MOSFET-based transistors were more stable in terms of temperature, but the time of around 1 second eliminates this solution in our bridge with the keys when we need to switch it on and off during research. That's all. And in next maybe in the future we will take into consideration only linear technology current source, maybe something like which is quite the same. We will take into consideration quite the same current sources which are integrated. That's all. Thank you very much.
Thank you. So, do we have questions?
This is analysis, so as a scientist you know how does it work. What will be your solutions as engineer to compensate these problems? Do you have it? Because you know, as scientist you want to know, as engineer you want to solve a problem. How you will solve the problem?
The best thing is to use integrated circuits, not circuits based on the different elements placed on the PCB boards. It's
some compensation,
maybe some compensation. Maybe we can use some, I would say, separation, thermal separation for current sources, which are placed on the PCB board. Because sometimes when you apply some supply to the circuit, this element can hit the PCB board. That is why we have to use some separation, thermal separation. That's a solution, I think.
Some questions? Thank you. So we not fit in time on first presentation. Maybe we will use some other. We have a presenter from China, yes. And the topic is hardware in the implementation of single iterated multiplicative inverse square root.
Okay, thank you, Chairman. Okay, ladies and gentlemen, good afternoon. Okay, we are going to today. I'm going to talk about the implementation. It means about traditionally we implement algorithms in software to do some process, and our project is focused on the inverse square root. This is the schedule. And first we were talking about the motivation and the development of some of the references. And second, we will analysis the different approximating methods of to implement the inverse square root. And finally, we will implement this method in hardware and doing some comparisons. And finally, we will show an application. Progress in digital signal and integrated circuit technologies. We have many arithmetic element functions, such as reciprocal, square root, and square root reciprocal. This project we will mainly focus on inverse square root. And as the development of real-time processing and acceleration of some complex algorithms is very necessary. So we have to find a trade-off between among these high procedure and maybe high throughput and with no cost. So the challenges is that how to build competitive solutions for these arithmetic element functions. And this is an example. We in the Cholesky decomposition, we implement in software. It will take up to more than 6 microseconds. So it's a long time. If we apply it in real time in application, such as in real time processing, so it's very slow. So we have to find some ways to accelerate. And there are some methods in realize inverse square root, such as table techniques and subtractive techniques and multiplicative techniques. The limitations of each method is very there are limitations such as cost and non-latency. Maybe the speed is very slow. This picture shows the some of the reference, the roadmap of the reference, and so the three techniques: table and subtractive and multiplicative. And we have made used some of the recently developed technologies. In the initial seed, we used multiple piecewise linear approximation, and we used quadratic convergence, Newton-Raphson method, and also we, in order to reduce the multiplier, we used the multiple constant multiplication. Okay, let's go to alleged methods. In the there are, I just have taught, there are several methods to implement the inverse square root. So we choose the combination of some of the techniques. This is the first is the initial seed. We use these equations. Use these equations to implement the initial seed. We use the three piecewise linear approximation. And we use Newton-Raphson method to to compute the result of the inverse square root. And this is the derivation of the Newton-Raphson method. Okay, this picture shows the comparison of different methods, the procedure. We have compared 5 methods, and just as shown in here. 8 piecewise linear approximation in highly linear range, and first order and single Newton-Raphson method, and the table techniques plus multiplicative method. We have compared the different memory bits. And M4 is the 3 piecewise linear approximation with single Newton-Raphson method, and M5 is the 4 piecewise linear approximation. We can see the average error different method has obtained. This shows the M1 to M5, and we can show the relative average error. Different methods has occurred. Finally, we will go to the hardware implementation. in our project, we have used this technology, a multiple constant multiplication, which means to reduce the hardware cost by eliminating some multipliers. This means use additions and shifts to implement multiplication. We have used a project developed by some researchers. Okay, this is the hardware architecture, which means this is CSE is MCM, and we also use this part to get the initial seed, and they use Lithuanian method to get the result, to compute the result. This table lists the performance comparisons of different methods. As I have just mentioned, we consult five methods in this part, and we implement all these methods in hardware and compare different cost, performance, and latency. We can see that Tempo has a competitive solution for many applications. Second, we have used these different architectures to in Cholesky decomposition. We have implemented different Cholesky decomposition and used the hardware architecture we have developed to compare the performance it has obtained. This structure used is a table. It's a table techniques. And this one we use the MCM techniques. And this is the proposed M4. We use 3-piecewise linear approximation with a single Newton-Raphson method. We also in this part we also use the MCM techniques. And this is the 9-order Cholesky decomposition. The result is listed here, and we can see that from this table we can see that when we use MCM techniques, it can have a performance improvement. Also, this one is improvement, yes. And let's come back to the first example we have showed. In Cholesky decomposition, we use the software and we use the hardware. The time it cost to process type line order 9. You can see that there is a huge speed up. Okay, the conclusion is that we used the combinations of the existing techniques, such as these ones, to yield a good performance trade-off for inverse square root, and the technique of MCM can effectively improve the hardware performance in terms of speed and throughput. Thank you.
If I understand good, you implement that in fixed point. Is it possible to implement good your solution in float point? Floating point.
Floating. The solution is okay. We have compared different architectures, and it's a trade-off. It's a trade-off to implement different methods. So it's hard to say which one is the best.
and it depends on your application. And we have used our proposed architecture in image processing, in compressed imaging. We use the table techniques and plus multiplicative techniques. So it's hard to say which one is the best. It depends your application, but in our research we found that if you use multiple constant multiplication, it can improve the performance, maybe or not. Okay.
Can you name some real-life applications that your technique can be used? In what kind of applications?
We have used in compressed imaging.
Video processing or what?
What?
Real-life application. What is the purpose of your technique? For what kind of applications?
Yeah, it's like this. We are developing compressed sensing the algorithm. We want to implement it in hardware also. So we find that there are a lot of data to process, and we will use inverse square root. So we focus on the inverse square root or not, and compare different architectures.
Okay, thank you. No more questions? Thank you. So the next presenter will be from Lithuania, Vitaly Novitsky, and the topic is design and optimization of pulse magnetic field generator for cell magnetopermeabilization.
Hello. So as you can see from the topic, our group is focused on bioelectronics, and to be more precise, we are focused on biomedical electronics to have biological applications to treat cancer cells, tumors, etc. So, first, the motivation. So one of the most known, let's say, biomedical techniques to use pulsed electric fields or pulse power electronics is electroporation. So the purpose of electroporation is to apply high pulsed electric field in order to induce sufficient enough transmembrane potential and permeabilize a cell. You could destroy a cell, you could increase the permeability to alpha molecules, drugs, to DNA, but the straightforward disadvantage that usually in electroporation you need electrodes in order to generate high pulsed electric field. And as a rule, these techniques are invasive. So you need to penetrate the tumor, generate the sequence of pulses, create some kind of protocol, and then you have permeabilization, reduction of tumor growth, etc. The method is economically good, wise solution. It has high applications in medicine. It's already made its way to clinical applications. So you could transfer drugs, genes, you could treat the tumor, you could increase the wound healing, and you could also apply this method in activation or sterilization of food process, in food products. But our group decided that we could, let's say, try or research or alternative method where you could reduce the disadvantages of electroporation, minimize them by application of pulsed magnetic fields. These are commercial devices like electroporators that could be, let's say, applied in both clinical research or in laboratory, and usually you need some kind of electrical pulse. With pulsed magnetic fields, we try to copy this, let's say, methodology. Therefore, we need to generate a pulse that should be well controlled. You could control the pulse duration, the pulse amplitude, the number, frequency of pulses, and as a result, observe the biological effects, the cause biological effects, both, let's say, in living microorganisms or in vitro, like you have a cuvette, some kind of sample, and just laboratory research. So we decided that we need high power systems, a device that can accumulate high amount of energy, and therefore discharge it controllably through an inductor. In our case, both the power generators and the inductors are self-made. They're developed specifically for each experiment, and each generator is in some kind is unique. But what you get with pulse power inductors, where you can generate pulse magnetic field, you don't need invasive techniques. You don't have electrodes, therefore you could treat the cells, you could treat the tissue non-contactlessly. As a result, potentially you could apply this method similar as an electroporation. So the parameters of our required generator that we want to have at this study. So our magnetic field should be like 4 to 6 Tesla. Based on preliminary data, we investigated and knew that these kind of magnetic fields, if they are fast enough, if they have high enough induced electric field component, they are good enough to induce significant detectable effects in biological cells. So as a result, our current should be in the range of 1 kiloampere. We limited our device to 2000 kilovolts, and that's based on the load calculation. And we try to increase the flexibility of the generator. So we could control the pulse duration, the pulse number, the frequency, and our volume of effect right now is 10 microliters in this generator, because this generator was developed for in vitro studies, therefore for fundamental research of, let's say, magnetoporation technique, which is alternative or in addition to electroporation. So this is the simplified circuit of the generator. We used 4 MOSFETs, 2 in series, 2 in parallel. We have capacitors, one faster, one is more inductive, but as a result we have high power, high energy accumulation. The most significant part is the inductor. We need to develop the inductor specifically for each experiment. Therefore, we need to control the number of windings, the volume of effect, and therefore always control and observe the distribution of magnetic field. For transient process compensation, since we are using inductive load, we need snubber circuits, crowbar circuit, and we use a shunt resistor to have an over-damped circuit response. Therefore, our generator would generate some kind of similar to square wave pulse, which is advantageous for electroporation or, in this case, magnetoporation. So the development of inductor was made in COMSOL multiphysics environment. So based on this model, we analyzed the distribution of magnetic field, induced electric field, and therefore, if the results are applicable, if the results are acceptable, we can develop the actual prototype. The problem with our inductors and with all solenoids that if we can get let's say homogeneous magnetic field, the problem was that the induced electric field is not homogeneous. So in each experiment, when we have observed, let's say, a response of the cells, like the cancer cells or any bacteria or any other cells, we need to account that the cell that was here experienced different effect than the one that was in the center. So the special distribution of cells in the suspension has an effect. And actually, right now, we have some kind of well-developed mechanism why it happens and how cells differently react both to magnetic field and to the induced electric field too. So basically we have 2 responses during one pulse. In this case, our generator was like up to 4 microhenries, and with the, let's say, 900 amperes, it could generate up to 6, something like that, Tesla. But this is a model data, simulation. We compensated the transient processes, so basically since our inductive load is dominating, we just compensated the overvoltages and induced voltages on the MOSFETs with RC circuits, and based on simulation data, and then experimentally just use the RC values that were found in the simulation. As a result, we are able to, let's say, have 2.4 kilovolts total commutating voltage of our, let's say, switches, but all the voltages were controlled, and we still had a reserve of 400 volts while the switches were successfully commutating. The measured pulse was like that. This is the influence of the compensation circuit. Obviously, we could go and make it a better square wave form, but the problem is that we have still risk if we use different inductor and wait for constantly switching inductors. You could have a too high voltage, and our MOSFETs will just burn. So we have this kind of transient process during our, let's say, generation of the pulse. Applied research. So we use cells. This is controlled. Sadly, it's not so well seen here, but you could see that the cells are slightly fluorescent. So we used a fluorescent marker that is not usually going to the cells. If the cells are, let's say, having good cell integrity, so the membrane is quite good, but after application of pulse magnetic field, after using of this generator, we can see slight fluorescence of the cells. Obviously, when we apply electroporation, so we use electrodes, we put the cells into the cuvette and apply electrical pulses, we see better fluorescence. Right now, all the available studies on magnetic operation show weaker efficacy of magnetic field, but the proof of concept has been already confirmed by independent groups in the world, and it's agreed that pulse magnetic field could be effectively used to actually permeabilize biological cells. And these types of pulse magnetic field generators are in high demand, because if you can buy an electroporator, there is no way you can buy a pulse magnetic field generator with the parameters that are required to actually permeabilize a cell. Usually magnetic field generators are like for stimulating of tissue, like transcranial magnetic stimulation or something like that. Our future prospects is to actually use this methodology in Viva. Right now we have a project. In this case you can see electrodes, so that's conventional electroporation, but we always need a reference. Since there is already a methodology that's, let's say, present on the market for 20 years, we always need to compare our new proposed methodology with magnetic fields with the clinically acceptable and right now popular electroporation techniques. In our case, we use planar inductors that allow contactless treatment of mice, of the surface, and hopefully will be successful. Thank you.
Thank you. So, questions, please? How the efficiency of magnet operation compares to sun operation?
It's weaker. I mean, right now, if you have, let's say, mammalian cells, you could permeabilize with the available protocols of our protocols, like 30% of permeabilization. If we use, let's say, high amount of pulses, so the sequence is getting longer, but then we should account for gel heating. With collaboration of groups from the European Union, from Slovenia, we were able to get 80% of self-permeabilization. But the problem is, let's say with sun operation or electroporation, you have a better molecular transfer. With magnetic fields, right now, the best we could offer, or any group that's working in this field can offer, that you have high permeabilization, but the transfer is really weak. Something similar is observed with nanosecond electroporation. So you can successfully permeabilize the cells, but it's hard to inject molecules inside. With magnetic fields, it's something similar. We already speculated about the electrophoretic forces that are induced in the suspension during our treatment. But right now, magnetic operation is weaker than sun operation.
But you never evaluate the percentage of permeated cells per joule.
No, that's typical for food processing.
In such case, it could be even less.
It's less.
What confuses me, can you go to your electrical circuit?
Sure.
Yes. Okay. What is the capacitance, total capacitance of C1 plus C2?
C2 is several microfarads, C1 is higher. So C1 is to actually to give energy to have high dBdt, and C2 is just to have the, let's say, like a filter.
Because according to the parameters that you have given, you need from 1 to 10 joule. So where they are coming from?
1 to 10, actually in the paper there is exact number of joules we have calculated. Have you multiplied by the microseconds?
I have multiplied by inductance, because the energy you need to excite can be calculated by current squared times inductance. Of course, it can be multiplied by time.
I mean, we have a shunting resistance to have an orthodynamic response, and this is actually an experimental pulse that is measured with the needle.
But anyway, it is experimental results, and
yes,
you have the confirmation that you have reached.
Yes.
Thank you.
Thank you. Thank you. So, next presenter will be from Turkey. And the topic is novel first order current mode MOSI phase shifters.
Okay, my name is Emre Arslan, I'm from Turkey. I will present my paper, which is about novel first order current mode MOSI phase shifters or all-pass filters. I will start with a small brief introduction, and then I will show you the proposed phase shifters, and then I will talk about the design algorithm very shortly, and then I will give the simulation results and conclude the presentation. MOS only stands for metal oxide semiconductor implementations. It only uses the MOS transistor and its parasitics. As all you know, if you want to design, for example, a filter circuit, you need resistors, capacitors, but MOSFET has some parasitic capacitances. For example, if it operates in saturation region, the gate to source capacitance is dominant. So the original idea stems from this point. Can I use this parasitic capacitance as a physical capacitance? Plus, it also has a GM value, a transconductance. 1 over GM makes a resistance, so can I use this as a physical resistance? This is for MOS only, but if you use a physical capacitance instead of a CGS value, for example, then this is called MOS-C or maybe GMC filter design. What is advantageous about this design is the low cost, low power, and also small chip area, because you only use the transistor itself. It only operates in high frequency ranges because you have very small capacitance values in femtofarad range. So the pole and zero frequencies are in very high frequency range. Okay, we use the parasitic capacitances and the GM value of the MOSFET as external capacitance and external resistance values. This table shows some filter circuits from the literature. They are first order all-pass filter circuits which use some active circuits. For example, current conveyors, current difference in transconductance amplifiers, and some active circuits. And these are the number of the passive elements that they use. They use capacitances, 2 resistors, for example, for this one. It includes 32 MOS transistors, and this is the layout area and the power consumption. But these two ones that we proposed here use only MOS-only circuits. We use capacitors here because I will show in a little bit later that we have to guarantee the transfer function of the first order filter circuit. We prefer to use MOS-C filter design in this paper. As you can see, in total, the core circuit plus the biasing circuit only consists 8 MOS transistors. And this is the layout area. As you can see, it is the smallest one, and the power consumption. These are the proposed first order phase shifter circuits. These are the core circuits. These are the AC implementations. They only include the core circuit. There are no biasing transistors around, as you can see. For example, the gate of this is connected to the gate of this one and the drain of this one, so there is no DC current flow here. This is only the core circuit, this is only the AC implementation. And this is NMOS implementation, this is the PMOS implementation. They are two different phase shifter circuits. And these are the transfer functions. As you can see, we prefer to use a physical capacitance here. This is for the NMOS implementation, and this capacitance is for the PMOS implementation. By connecting this, the drain current of this transistor give me an all-pass filter transfer function, this one. And the drain current of this transistor over the input current also gives me another all-pass filter transfer function. These two are core circuit plus the biasing transistors. These 3 transistors are the core circuits, and another transistors around are for DC biasing purposes. This is the total implementation. It only consists 8 MOS transistors, so it have a very simple structure. If you prefer to use this one, this is the load resistance. It must be connected between the drain of this transistor and between the DC power supply, VDD. If you prefer to use this one, the only difference is this. You can use a grounded resistor as a load. And for a MOS-only design, if you take into account the CGS values of all the transistors like this, you will have a complicated transfer function like this. But if I assume that the physical capacitance that I connected is much more greater than the gate to source capacitance, and also if I can assume this equation, this reduces to the easiest transfer function like this. After these assumptions, the transfer function looks like this. So it's a first order all-pass filter. And these are the transistor dimensions of the phase shifters. They are obtained from the design automation tool that I will talk about in a few minutes. The width and length of the transistors are all obtained from using the design automation tool. How does this design algorithm work? I have some specs. For example, the center frequency, the Q value of the filter circuit, the gain, the input impedance, and also the output impedance. I take these ones as inputs, and I generate the bias currents, bias voltages, and aspect ratios of the transistors. These are my inputs, and these are the outputs. First, we start with using mathematical software tool. We model the transistor as a voltage-controlled current source. As you know, the small signal model of the MOS transistor is a GM times VGS current source plus the capacitance, the parasitic capacitance between gate and source, CGS. It's a 3-port device, and in each case, we randomly connect the MOS transistors. And in each case, we also generate the transfer function. If the transfer function gives me a first order filter circuit, then I select this one. It's a candidate. I again rerun the circuit, the software, and it regenerates another topology which is randomly connected. And if the transfer function gives me another first order filter circuit, I also use this one. It's another candidate. Then I generate the netlist of these candidate circuits. After the netlist generation, I use another MATLAB script. This MATLAB script takes my inputs or the user specs and then generates the aspect ratios, the bias currents, and bias voltages. These are the specs of user specs: power, area, center frequency, the Q value. And then the design automation tool generates me all the physical quantities, the aspect ratios, bias voltages, bias currents. These are the values of the simulation results, the supply voltages, and these are the simulation and calculation results. Measurement results are obtained from the SPICE simulations, and calculation results are obtained from the design automation outputs. As you can see, they are very close to each other. These are the simulation results, gain and phase responses. As you can see, the gain changes from 180 to 0, and 0 to 180, because one of them is an inverting type, first order all-pass filter circuit. What is good about this circuit is you can change the pole frequency by changing the biasing voltage. For example, the pole frequency is easily controlled by the bias voltage from between 7 megahertz and 11 megahertz. So it's possible to change the center frequency by only changing the biasing voltage. Time domain simulation results. For 10 microampere peak-to-peak input value, we only have 1% total harmonic distortion for NMOS implementation and 3.6% total harmonic distortion for the PMOS implementation. These are the corner analyses for small, fast, and typical transistors that we use. As you know, they are the even corners. And these are simulation results for these 3 different transistor models. And finally, Monte Carlo simulation results. We changed the value of the capacitor, the physical capacitor that we connect, and also we take into account the transistor mismatch values. To conclude, we use Mathematica, MATLAB, and also LT-SPICE to start, we start from modeling the transistor as a 3-terminal device, randomly connected them, generating the transfer function. If it is candidate, we use MATLAB script to generate the outputs using the user specs, input values. Then we make some LT-SPICE simulations and want to see that if the candidates are working properly or not. These softwares or the scripts can also be used for MOS-only design, not only for MOS-C or GMC, but we also use or propose some MOS-only filter circuits using these scripts. Okay, this is the end of my presentation.
Thank you.
Thank you.
Questions, please.
The capacitor that you are simulating, it is nonlinear?
It's a linear capacitor. It's a 5 picofarad capacitor. Yeah.
Is it parametric?
No.
What makes you think so?
By doing simulations.
No. What makes you think? Because I would expect CMOS capacitor to be nonlinear.
Yes.
What makes you think that it is linear? It is non-parametric and linear. Why are you making this assumption?
We obtain the transfer functions. The transfer function says me this CGS capacitance must be much more greater than the other two. So there are 2 ways. The first way is to make this transistor very large, and the second way is to connect a physical capacitor to these floating capacitor to these points. So we prefer the second one. If you make this transistor very large when compared to other transistors, so you can also obtain this transfer function.
Okay, thank you.
More questions? No? Okay, thank you. So, we have one more presentation from Poland. The topic is electromagnetic compatibility of impedance source inverters.
Thank you very much. My name is Krzysztof Bernacki. I come from Kaunas University of Technology, and today I want to say something about electromagnetic compatibility of impedance source inverters. First of all, I say something about impedance source network and difference between impedance source network and the impedance source inverters. Then something about motivation, then answer investigation, results, and a few words about conclusions. Okay, what is it? Impedance source network. It is a new DC-DC converter, and why I said that this is new? Because the first article is proposed for Professor Peng and called Z-source inverter in 2002 and 2003. Is this two article? What is different between impedance source network and the impedance source inverter? Because impedance source network is only structured DC-DC converter, and this converter can working with voltage source inverter or current source inverter. So if we connect impedance source network, this is the fundamental structure, Z-source inverter. If we connect the Z-source inverter with, for example, voltage source inverter, we have a impedance source inverter. Okay. How impedance source network working? In all impedance networks, the energy is stored in the inductance in a shoot-through state, which is implemented by switches in the half-bridge inverter. It's zero state. Zero state is the time when the input voltage of the output filter LFC is zero. Of course, now we have, for example, now we have 30 different impedance source networks. If somebody wants to know something more about structure, please find this information in Professor Peng publication. It's very good one's publication. Another structure is, for example, quasi Z source, cascade quasi Z source, LCCCT quasi Z source, and for example, delta Z source. Okay. In our research, we use only constant boost control. Is the basic method to control impedance source network. This solution characterizes the coefficient dz is shoots through state is constant. Why we choose this one? Because we want to analyze only influence to structure and don't analyze additional influence. And of course, many another methods you can find in another very good publication is Professor Peng is second part review of control and modulation techniques. The author of structure presents disadvantages and the advantages his solution. They describe solution dedicated to reduce problem with electromagnetic compatibility. However, in the literature, no one has performed comparative studies to several structure. So, in novelty in this research, in this paper, is present the results of the research on conductive disturbance and radiated emission to 5 selected with us impedance source network. This compare were performed in certificate AMC chamber along with a discussion in these results. Okay. Compare 5 structure. Yes, why this one? Because this is the first structure. This is the most simpler. As we can see, they have two capacitors, 2 inductor, and 1 diode. This is the Z source. This idea belongs to Professor Peng. This one is a quasi Z source. It's the similar. Is only one change because this diode is in this place. This one have a discontinuous input current. This one have a continuous input current, and this one idea belongs to Professor Peng and Professor Anderson. Another one is LCCT. This one have a transformator, and this one. The idea in innovator inventor. This one is Professor Strzelecki and Dr. Adamowicz. This one is cascaded quasi-Z source. They have a much more boost factor than another. And this one idea belonged to Dr. Strzelecki. And the last one, switching inductor Z source, this one, the idea belonged to Professor Zuo, Luo, Yu. Okay, every structure have another parameters. The most important is boost factor, number of elements, common ground, and that the structure have a continuous input current or discontinuous input current. And the investigation, the whole test performed in the Zephyr chamber according to standards under the supervisor in authorized to conduct such research. All tests were carried out of the two loads, 37 ohm and 2000 ohm. Why? Because we don't want to analyze additional influence to, for example, dynamic loads or RL loads. Okay. The analyses which were conducted of disturbance levels and radiation emission began determining the efficiency, the disturbance, changing the modulation dip M without impedance, and we know that changing modulation dip M doesn't matter for this research. This is our device under test. Yeah, I must say that our research as our comparative relative ones, the standards do not specify the recommended methods to compare characteristics. And as we know, in commercial work, only test results is defined. So if somebody have a good one, the system is according the standards. Don't have a problem. If have remarks, must redesign the system. But standards not say how we can compare our results. So the method used to compare the results is based to average of the results of for the entry range, as well as division into comparms and analysis of the record average local maximum value. Okay, what we get, what we have, as we can see, we have lots of results. In our research and our paper, we present only the worst case. And if we want to focus on these results, we can see that fundamental Z source inverter have the background is higher than, for example, quasi Z source, but it's quite different to analyze. The same situation we have in radiated emission. Only we can see the switching inductance Z source inverter have a much higher results. So in our paper we have a few tables when we have of every results, but it's necessary now it's conclusion. Conducted disturbance. The highest average level of conducted disturbance were obtained for the switched inductance and Z source inverters. The highest average value recorded for the local maximum was determined for the Z source structure. The lowest recorder levels of conductance disturbance were observed to cascade quasi-Z source and LCCT quasi-Z source. And the results of the comparison of the Z source and quasi-Z source using the analysis of the same value shoots through the Z coefficient present the potential to reduce conducted disturbance during when using a centralized ground as working with continuous input current. Radiated emission, the results discredited the switching inductance Z source inverter structure. The lowest recorded maximum level of radiated emission was obtained for LCCT Z source, quasi-Z source. No significant difference in the levels of interference between structure Z source inverter and quasi-Z source structure were registered as we can see case during the analysis conducted disturbance. The recorder mean level of the quasi-Z source structure was lower in comparison with the level obtained for switching inductance structure. Conclusion: the description of the result will help a designer to select the appropriate structure and what structure to choose. Structure with centralized connection to ground, structure with continuous input current, structure with cascade structure, and a structure with smaller switching elements number. Okay, thank you for your attention.
What confuses me, yes, you did not pass the electromagnetic compatibility.
Yeah, yes, yeah, of course.
Did I hear you right that you were using zero voltage switching?
No.
We
only voltage source. Only we use voltage source inverter with impedance source network. It's normal. No zero voltage switching or no frequency resonance.
Have you analyzed what is the reason of such high emissions?
Yeah.
Have you analyzed the topology or maybe you did some modeling? Where should this noise, electromagnetic interference should be coming from?
Yeah, we have one in this one. Every energy in all structure, the energy is stored in inductance, and we switching this inductance, and as we can see, this one is current choke in the inductance. So if we have 1 volt in one step, we have we have 1 ampere in the one step. So 1, 2, 3, 4, 5, 6, 7 ampere, and this is the main reason for this problem we think about.
How was the current measured?
How did
you measure the current?
In
the near field probe?
Yeah.
Okay, thank you.
And how many samples of each structure you tested?
How many?
Samples?
5.
But different 5?
Yeah.
One structure, one sample?
One sample, 5 different.
But only one sample of
yeah.
each structure?
Yeah.
More questions? Okay, thank you.
Thank you very much.
And the last but not least, I think, presentation will be from Czech Republic. Yeah? And the topic is universal pseudo-differential filter using the DCC and DVCCs.
Okay. So, ladies and gentlemen, welcome to my presentation about the research of our group at Czech Republic that we are doing. and dealing with the area of frequency filter design, so a topic very close to Emre, who was giving the speech about all-pass filters. So here in this case about current conveyors, which is the CC standing for. The presentation outline, I will just shortly describe the idea which is behind the description or the labeling of pseudo difference. What does it mean actually, or how at least we understand that? And based on that kind of idea, I will show you and briefly describe a frequency filter that we have designed using this current conveyor, and did also experimental measurements on that kind of circuit and how it works. So from the theory, we should know that we call differential circuits such as that we speak about differential input voltage and differential output voltage. We speak about differential voltage gain, and we expect that next to this mathematical description, we expect that also the inner structure is differential. This is shown simply here on a small, simple RC circuit. So this is what we understand as differential circuit, or also called like true differential, because everything is differential inside. But on the other hand, we can speak also about differential circuits in such a case that yes, we have the differential input and differential output and the differential voltage transfer, because this is only what the math says about differential circuits, and have the inner structure actually single-ended, and at the end result with a more simple structure at the end, because just from this simple circuitry we can see that here we have to use two resistances, and here is only one sufficient. Like the point is that if we would be able from just this simple RC circuit create a differential circuit one, or obtain differential input and output, for sure not. But this is the idea behind of pseudo difference circuits. What we used in our research or in our group, so we are all the, let's say, offsprings of Professor Weber, who was dealing with the area of current conveyors, and we somehow continue in that. And we used in this particular design two types of characteristic elements from this group. One is differential voltage current conveyor, and the second one is differential difference current conveyor. Those who know are very familiar with these equations. Who don't know that, the point is that there are unity transfer voltage and currents between individual terminals, described as shown here. Here we have the final solution, where we can see actually the core of the filter, frequency filter, where you can see that actually yes, it is just a simple structure, single-ended. There is no differential operation observable just from that, but feeding the circuit in appropriate way and obtaining different responses and doing a difference between them, we are able at the end to obtain various transfer functions. In this case, we obtain all the basic 5, so from the high pass to the low pass of the second order, and this is what the theory says, that yes, it should work like that without any problem, and really we can just apply differential voltage here, and from a selected pair of the output nodes we can obtain at the end the required differential voltage response. Above that, what we deal with is the analysis of parasitic properties of the active elements that we use, because they are not ideal. And in this case here we show the influence of parasitic impedances of the input and output terminals. And here we can see that yes, you are just, or you cannot stake on the ideal mathematical equation and count the values of passive elements and so on. Just you select few of them. There should be always something behind. And here we see how the transfer function of the high-pass filter here in this example changes the main parameters that we are looking for. So for example, here is the change of the theoretical and true center frequency, and here it's visible the maximum attenuation in the stop band of this high-pass filter, so at the lower frequencies than the center frequency. And so from these plots we can actually provide an convincing fact that yes, what should be the values of passive elements to use for later design. So in this case, like if you would like to obtain the maximum attenuation in the stop band, then we would have to go for the highest values of capacitors as possible. But then if we do that, so in that case we are in this corner of the 3D plot. So we will obtain an error in the center frequency, let's say by this 15%. We don't stop at the level of simulations, or not mostly. We try to use the chips that we have of the universal current conveyor, which is able to emulate these types of active elements of the current conveyors that we used in this design. And this is actually the result, and as a hardware. And here we have the result and comparison between simulations and practical measurements, where we know these equations quite well, which describe the ideal behavior, and define, or using them, we can define or determine the values of passive elements in terms of the pole frequency and the dipolity factor and so on. And based on that, and using these 3D plots, we can actually say, okay, the most suitable for our case could be the C1 and C2 to have 1 nanofarad, and all the resistors are determined from these equations. And here we can see the expected results. Next to that, which is like a marker, let's say, of these differential circuits. So we describe the common mode rejection ratio. In this case, we obtain for all responses, let's say roughly the 35 dB, that value. If we go for true fully differential, so we have like 80. So there's 50 dB difference. But the only problem in this case, as we can or could observe, is the error between these two voltage transfer to this X terminal. So during the design we can say, okay, once we would go for these structures, so everything can be almost rubbish, but this is the most important part, this section, and that will, if we design this input section very well, then we will reach much higher common mode rejection ratio, even using that kind of simple structure. Then just to sum up, there is the THD of the input signal, and here we should know that the current conveyors are supplied with the voltage plus minus 1.65 volts. So we go, or we are below 1% harmonic distortion with this 1 volt amplitude, so more than 50% of the supply voltage. So to conclude, I was just briefly talking about what's the idea of pseudo-differential filters and how beneficial they could be in terms of true differential systems to provide actually the same features with less complex structure. and we show that not just by simulations but also by experimental measurements. Thank you for your attention.
Thank you. More questions, please? We don't have. Can you open 9 slide?
9?
Yes. Can you
Yes.
explain the difference between this black one?
The black one?
Because
Yeah.
most of them fit.
Yes, yes, yes. So the difference here is caused by the fact that here, when we analyze the non-idle parameters, so here we analyze just the parasitic impedances of the active elements and assume the inner voltage and current transfer to be unity, to be ideal. So this is actually the main problem, because if we would understand also here non-unity, this voltage and current transfer, so this would be huge, and we couldn't be able to analyze it that simple. So this is the main problem, that here we can see that that we go for 1 nano and 1 nano, and so we should in theory end up somewhere here with the attenuation of somewhere between 60 and 70 dB, but end up later just in theory just below 40. And with these measurements, the second issue is that in these simulations we use the typical parasitic properties of the active element itself, and once we go for the design, then we take a chip and we didn't measure the true values of these parasitics, so we get a bit above, so it's like that.
No questions? Thank you. We finished just in time, and thank you for your attention, for your questions, and now I think you deserve a cup of coffee.
about electrical engineering. First is from China, Yun Liu. Yeah, please present your presentation. Your topic is allocation method for mobile charging vehicles based on the special charging demand.
Okay, good afternoon, ladies and gentlemen. I'm Liu Yujun from Southeast University in China, and I'm glad to introduce our work about allocation method for mobile charging vehicles based on the spatial charging demand. Our work is mainly about three parts. The first part is a new charging mode. We call it mobile charging vehicles. And the second is about the forecast about the spatial charging demand. And the last, we will introduce you a location method for this vehicle. So why we want to do this research? As you know, the electric vehicles in Beijing and China is developing very fast. Many buses in Beijing city has been changed into electric vehicles, and many people buy electric vehicles to, and they can get a little subsidy from Chinese government and our power company. So we need a lot of charging facilities to charge these vehicles. While in China, there are not enough charging stations for all the electric vehicles. And we found that most of the charging stations in China, it can be found idle because they are too far from all the EV users. So we want to, so an idea come to our mind. This idea we called mobile charging vehicles. We want to use this charging vehicle to charge all the EVs. Then I will introduce you what is mobile charging vehicle. You can see this is a map of a traditional parking lot. And the pink one is mobile charging vehicle. And this truck may take maybe 6 or more charging tanks, charging cells in the truck. And when a EV user drove into this parking lot, he can tell us when to charge his vehicles. And the worker of the mobile charging vehicle will use the charging cell to charge his vehicles. This brings us a lot of advantages. The first of all is that mobile charging vehicles takes much less space compared with traditional charging station, and so we will save a lot of money for the Chinese government and our power company. They don't need to build charging stations anymore. And because of the drivers will told us when to charge his electric vehicle, so we can get a lot of information of their charging behaviors, and we can move this mobile charging vehicle to different places according to different real-time charging demands. And we found that in different time, the spatial charging demand is different in the city. So at first, we want to forecast the charging demand. Then we can, with the result of the charging demand, then we can allocate all the mobile charging vehicles. To forecast the spatial charging demand, we use a theory of travel chain. This travel chain shows us the travel behavior of a citizen from the morning to the evening. And we use this method to simulate nearly all the Beijing citizens, simulate their charging behaviors according to Beijing annual travel report. The data is all from this report. And then in this function, this is a map of Beijing. We divided into more than 700 grids. Different grids shows different functions. We put this grid, divide this grid into different areas. Most of about commercial areas, working areas, and resident areas. Different areas have different road conditions in the map. So we fill the grids with different colors to show the road condition of different grids. And with the charging behavior and the map, we can know where we can forecast the charging demand. The red shows that there are a lot of charging demand in this grid, and the blue one shows there's much less charging demand in this space. With the map, we can do this research and we will find the place to allocate all the mobile charging vehicles. Our object function is to find the smallest distance between the EV users and the charging vehicles. And we use a lot of constraint condition to simulate the situation in Beijing. Then you can find these stars in this map. This is a result to allocate all the mobile charging vehicles. As we see, in the time before 15 o'clock, we need more vehicles to cover the demand of different EV users. And after 15 o'clock, we need less vehicle to cover the needs of all the EV users. With this research, we can use mobile charging vehicles to fulfill nearly 80% of all the EV users to charge their electric vehicles. Okay, thank you very much.
Thank you for your presentation. Have you any question, please? So I want to ask a question.
Yes.
One question.
Yes.
Have you any application for this study?
We haven't put this into a demonstration. We only research it in theory.
Okay, thank you. Our second presentation, Clementa. Okay, welcome. Your presentation topic is most swarm algorithm for solving combined economic and emission dispatch problem.
Yeah.
So, go on, please.
Just to try this equipment.
Okay, it's no problem.
Okay.
I hope it is not long presentation.
Presentation is long,
It is crowded.
but I will try to be short.
Okay, please.
Briefly to present
Okay.
our common work.
Okay.
I'm Dardan Clementa, and I'm coming from Serbia, and I'm with the University of Pristina in Kosovska Mitrovica, exactly, Faculty of Technical Sciences. And I will present now this paper. What was our main task? To do minimization of the fuel costs and emission of in thermal power plants. Also,
the main proposal, the main aim is application of this Moth swarm algorithm to the combined economic and emission dispatch. And what we solved: minimization of fuel cost, minimization of emission, and third problem which we solved also was minimization of fuel cost and emission at the same time. Optimal distribution of generators output was determined. Function describing the dependence of gas emission and fuel costs on generation output power have complex shapes. And this paper aims to propose the procedure for solving this CED problem by means of the Moth swarm algorithm. For example, first objective function which is to be minimized is presented in this slide. And this function represents one quadratic function. On the next slide, we have the second objective function, and this relates to the second optimization problem. And no, this is the first one, but expanded by a valve point term. And that means that is combination of quadratic and one sinusoidal function. This is first objective function. The second one is presented in this paper, and is presented to emission of toxic gases. This function is also free. The three first terms represent a quadratic part, but the last one represents an exponential part. Parameters appearing in the second objective function are listed below. In this slide, we can see objective function which is optimized in the third optimization problem. That means we solved together we performed the optimization of both fuel cost function and emission function in the same time. And how we did that? Using weighting factors and scaling factors. For example, if weighting factor is equal to 1, that was the first case of optimization and relates to fuel cost minimization. If weighting factor is 0, that means the second optimization problem. If we consider the third one, weighting factor was in our study 0.5. For example, constraints appearing in our optimization problems are related to generator capacity, and of course power of generator is between two limits, minimal and one maximal, and a different constraint is related to a known limitation. That means in each power system we need to have power balance between generation and consumption. According to this slide, we can take a look in expression related to losses in the system. That means we could consider problems without losses and with losses. For example, if losses are taken into account, that means generation is located on different parts of a power system. But if they are equal to 0, that means all generators are located in one thermal power plant. Due to the fact that application of this algorithm was only our work in this study. More details related to this algorithm can be found in reference 37, which is numbered according to the paper, which will be printed after this conference. And also this is one of the newest algorithms corresponding to meta-heuristic population-based methods. The paper 37 reference is reported in 2017, and for example, from all information related to this algorithm, we selected just two pictures to show this time. That means first picture relates to the case then moths fly nearby to the light source, and the second one relates to the moths which fly not directly towards the moon, to the moon, but they intersect rays coming from the moon. And more details, of course, I don't have time to talk about them, can be found in this reference 37. Simulation results are presented in a few next slides. For example, we tested two systems. First system consists of 6 generators, and this is one standard IEEE 30 bus test system. The second one is with only 3 generators, also a standard test system. First case, first test system was considered for 2 cases. First one is without losses, and the second one with losses. I will return my presentation some steps back. For example, if losses are added to considered in the problem, they are added to these expressions. That means to this one and to this one at the end. And that means we consider generation located in different points in the power system. If in case then generators are located in the same power plant, that means these 2 equations, that means 2 and 3, labeled with 2 and 3, corresponds to the case without loss. And now, in the same time, we compared our results with some different meta-heuristic algorithms. That means with Firefly algorithm and hybrid particles form optimization gravitational surge algorithm. Usually, scientists perform 20 runs, but we in our paper performed 30 runs for each simulation. In this first table, table 2, results relates to the minimization carried out for the cases then weighting factor is 1, weighting factor is 0, and this the 0.5. That means first column on the first case correspond to the minimization of fuel cost function, the second one, and so on. But case 1 is with losses, and the second one without losses. Results related to test system 2 are presented in this table. Also the best solutions. According to table 3, the minimum values of the fuel cost and emission are the same for all the 3 algorithms which are tested in this study. by comparing the standard deviations obtained for all the three algorithms. The standard deviations related to applications of the mod swarm algorithm are by far the lowest. Table 4 shows the best solutions for the power output, fuel cost and emission of the test system 2 obtained by means of the MSA for the cases, of course, for all the three cases. This table has also the second part. Yeah. Related to the case 2. Also, you can see our algorithm which is applied here is compared also to other references, but due to the lack of space we cannot give more information on them. Simulation results from the table 5 give from them we can see the following. The MSA and the FFA provide better values than the minimum for the minimum fuel costs compared to the listed references. Also, these two algorithms gave the same or very close results obtained by algorithms reported in 18 and 35 references, also which are listed in our paper. And also minimum value of nitrogen oxide emission calculated by the two algorithms is the same or better than associated results reported in the listed references. Simulation results presented in the next following next three slides represent comparative profiles of algorithms used in this study. And from on all three, solid line represents curves, profiles related to the MSA algorithm. And also conclusion is MSA gave the best values related to standard deviation. Some remarks related to simulation results are presented in this slide. And now I reach my conclusion list. The application of the MSI to this combined economic and emission dispatch problem has been proposed in this paper for the first time. That means first application. The algorithm has been successfully tested on the two standard IEEE test systems. The comparative analysis of the results obtained by means of the three algorithms show the standard deviations of the results that are the lowest for the indicating a large degree of robustness for the MSI. Moreover, the algorithm generated the minimal values of the fuel costs and also nitrogen oxide emission that are the same as the corresponding results of the two algorithms used for comparison. And these minimal values are better than the associated ones that are obtained using the recently developed algorithms. The convergence profiles also, I said previously, are the best for the MSA. And that is the end of my presentation. Thank you.
For your presentation. Any question? No question? Yes?
Tomasz from Kaunas University of Technology. If I understand it well, you use a power flow computation and you just use this your algorithm to set some parameters for power flow computations.
Some
power flow. power flow program for power flow computation. And you use your algorithm to set some.
We developed algorithm by authors of the reference 37. This is not our algorithm, but we are authors which for first time applied it in this combined economic and emission problem of optimization.
Okay. Did you check this algorithm for the bigger system?
No, just these two standard test systems, and this is usually procedure. If you solve for the first time any problem of this kind, you use IEEE bus systems. For example, this with 30 bus system is larger than the second one,
yes,
with 3 generators.
I have some experience with optimization of it was reactive power optimization, and it was a huge difference when I had a 30 bus system and I need to do optimization for a couple thousands of bus.
Appearance of this large or high differences between results are normal for this kind of application of meta-heuristic algorithms. We solved also different problems with different algorithms in the past, and also one way is to find meta-heuristic algorithms developed by other scientists which give similar, or how to say, algorithms giving the same results. But what is advance made by us? Advance is this standard deviation in our case related to the solving of this seed problem. We got better results than, for example, Firefly algorithm and the third one.
Thank you. Later you can discuss.
Yeah, I'm ready for discussion.
Yeah. I have another question. So I want to ask one question, only one question. When we compare this study to others' works, what is the main novelty of this study? For example, all of works related to simulation or real conclusion?
At the beginning of my presentation, I was a little bit confused, but I forgot to say the first application. The first application related to solving of combined economic emission dispatch problem and optimization of this is the main contribution. After that, also adaptation of parameters and comparing to other algorithms made and presented here.
Okay, thank you. Thank you.
Thank you very much.
Our third presentation from Czech Republic. I think only Czechia. Roman Hirbak.
Good afternoon. My name is Roman Hrbáč and I work at the Technical University of Ostrava, the Czech Republic. I have the paper deal with the development of the smart annealing unit as well as the analysis of low frequency conductive disturbances arising when it is connected to the low voltage public network. I would like to give you a brief outline of what our team has been working up on. The main task of the annealing unit is to control annealing process, which is a kind of thermal processing of metals carried out in order to improve some properties of materials, especially steel. Annealing improves surface hardness and its machinability. It also decreases internal strain. For several years, our department has been cooperating with the company Svar Service Limited on the development of annealing units. During this time, they have undergone several innovations. The first innovation of the annealing unit was replacing the simple control which uses electromechanical contactors, a more complex control using power thyristors. This figure shows a photograph of the first innovation of the annealing unit. The upper part of the picture shows control electronics and below them then there are thyristors. The next innovation included a requirement for the entire modernization of the unit by means of intelligent control. This involved complete replacement of control electronics with a programmable logic controller and control unit for each annealing section. This innovation also meant another modification of the power unit parts, and the thyristor previously used were replaced with the solid-state relays. Figure 2 shows a block diagram of the modernized annealing unit. The annealing unit consists of following main blocks, such as industrial computer. This is here, and programmable logic controller and its parts, and microcontroller control units for 6 sections. The control unit can regulate the heating power by continuously changing the current. They create a suitable algorithm for switching the power semiconductor elements, and the algorithm changes on the basis of the current values measured by the control units, as well as control commands from a superior programmable logic controller. To switch it algorithm I used. The first is phase control algorithm, and the second is full wave control algorithm. The prioritized algorithm is full wave algorithm, provided that the maximum load current does not exceed 200 amperes. This corresponds the load current of 65 amperes in the time of 8.7 milliseconds at the last zero voltage crossing. Figure 3 shows startup procedure of the annealing unit. As you can see, the value of the current pulse tested during the time of 8.7 milliseconds reached 65 amperes. Therefore, the control unit uses a phase control algorithm for switching the power semiconductor elements. Figure 4 shows another example of startup procedure of the annealing unit. As you can see, the value of the current pulse tested during the time 8.7 milliseconds didn't reach 65 amperes. Therefore, control unit uses full wave control algorithm for switching the semiconductor elements. Figure 5 shows the process of the annealing cycle for annealing the weld, a thin walled tube. Further, the graph illustrated the actual annealing current generated by the control algorithm. Figure 6 shows simplified diagram of the measurement stand. The measurement were carried out on the prototype of the annealing unit uses the network quality analyzer. Yes, I'm sorry. Figure 5 shows total harmonic distortion of the low voltage network measured during the phase control of the annealing unit. The required value of the current was 30 amperes. The total harmonic distortion of voltage was 2.34%, and total distortion harmonic of current was 33.77%. Figure 8 shows total harmonic distortion the low voltage network measured during the full wave control. The total distortion harmonic voltage was 1.74%. The total harmonic distortion harmonic of current was 4.82%. Figure 9 and 10 show phase voltages and phase current for both control, phase control, and on the left side and on the right full wave control. Figure 11 shows annealing unit. Upper part of the picture shows control electronics, and the lower part shows protection of the annealing unit. Figure 12 shows an example of experimental measuring during the full wave control of the annealing unit. Here is industrial computer, and as you can see, control electronics. The whole development of the annealing unit was carried out in order to achieve the best parameter of annealing process. Another goal was to achieve maximum reliability and to minimize the disturbing effects on the low voltage public network. The conclusion from the experimental measurements carried out on the annealing unit prototype and from their analysis is as follows. If full wave control is used, the occurrence of harmonic components of voltages at currents will be reduced. By problem is this causes a flicker effect. The extent of the negative effects depends on the short circuit ratio of the supply network in the point of connection. The EMC standards cannot be met when using the wave control. However, solution is to use active harmonic filter.
Okay, thank you for your presentation. Have you any question, please? No? So, I want to ask.
One question. Why you removed thyristor before SSR? Instead of thyristor, you used
solid state relays.
Why? Why you removed?
I don't understand.
Firstly, you used thyristor.
Yes.
Then you removed thyristor. Instead of thyristor, you used
solid state relays.
Why you removed?
Why? Because they are cost lower.
Cost lower. SSR, I think it is expensive than thyristor.
Mm-hmm.
So.
Yes.
But cost is increase, become increase.
Of firesters of solid state relays.
Maybe decrease the Your power is high?
Yes.
Maybe decrease the total harmonic distortion? Switching? What is the frequency of your switch?
Parisa 40 hertz is switching for us.
Switching frequency?
Yes.
Yeah.
Only.
And I suggest near switch, most controlled thyristor. Instead of SSR, you can use, okay. Okay, thank you. Now, our presenter, Hamza Farura from Algeria. Okay, please.
Good afternoon, everybody. My name is Hamza Farura from University of City of One, Algeria. I'm glad to present to you my work, which is entitled Finite Set Model Predictive Direct Power Control of a Grid-Connected Current Source Inverter. My presentation will have displaying first introduction, then description of the current source inverter, topology and model, and then the global system configuration, which contains two parts, sliding mode observer and model predictive control MPC. Simulation results are discussed in the fourth part, and then conclusion. First, introduction. Renewable energy resources are clean, free, and abundant in the nature. These power sources are heavily dependent on power electronics for control and conversion. All of you know the voltage source inverter, but in the recent years, current source inverters are direct competitors of voltage source inverters due to many features they offer. Among these advantages, high reliability, short circuit protection, and low harmonic distortion of output currents and voltages. And the most important advantage of current source inverter is the ability of boosting output voltages. Despite these advantages, CSAs have some drawbacks, especially the complexity of the control schemes. This work contributes by proposing a new control strategy for current source inverters, which is based on direct power control and model predictive control, named finite set model predictive direct power control. A current source inverter is composed of a current source which is in reality doesn't exist. We can replace this current source by in the laboratory by a DC source and an inductor. It contains six unidirectional switches, an IGBT in series with a diode, and the output capacitor filter, and the load, of course. At any given time, the current source inverter needs to have one of the upper switches and one of the lower switches conducting simultaneously to ensure a path of the current source. This restriction can be summarized as follows. Using the switching functions, the three-phase currents, output currents of the CSI can be given by these equations. By converting this into a vector, we get the current vector, the output current vector of the current source inverter. We have 9 possible combinations of the switches, which gives us 6 active vectors shown here and 3 null vectors. This is our control scheme, the global control scheme. First, we measure the grid voltages and currents. These measurements are then transformed into vectors. These 2 vectors are introduced into the sliding mode observer in order to find the capacitor voltages without sensors, just by observing them. These 3 variables are then introduced into the predictive controller, which generates the 6 control signals to the switch of the CSI. The system model can be state space model is given by this 2 equations. This is the single phase representation of the system. Usually in observers, the error between the measured and the estimated value is fed back through linearly. But sliding mode observers, the error is fed back through a sine function. So it is fed back via discontinuous switched signal, as you can see here in the model of the observer. This is the sine function. The sine function has a problem, which is the shuttering problem. To avoid this problem, we introduce a saturation function instead of the sine function. The saturation function is given by this equation. And you can see here, it is, you can see the difference between the sine function and the saturation function. Model predictive control uses this, the system model in order to generate the optimal control signals. The main idea of MPC is the determination of the required signals in advance, and it has a lot of advantages, especially in power converters. One type of model predictive control is finite set model predictive control. In this type of predictive control, the system model is derived and predicted in the next sampling period, and then by using a cost function, the cost function is used to generate the optimal control signals. Finite set model predictive direct power control is based on the DPC, direct power control, and model predictive control, where the active and reactive power are predicted for the next sampling period, and then the cost function is introduced to find the best switching combination for the power switches. A prediction model. The active and reactive power can be written in function of the grid currents and voltages in the synchronously rotating frame alpha beta as follows. And it can be written the prediction of the powers in the next sampling period by only changing here in the instant k and here in the instant k plus 1. So to predict the powers, the active and reactive power, we only need to predict the currents and the voltages, the grid voltages. If we predict these 2 variables, we can predict the active power and the reactive power. For the prediction, we use this approximation, such as for a variable x, the derivative of x in time can be written as follows, where Ts is the sampling period. The application of this approximation into the state space model of the CSI gives the prediction of the current. And on the other hand, the grid voltages can be easily predicted by shifting only the grid voltage by theta. This picture and this flowchart will summarize all the control technique. First, the measurement of the grid voltage and current and calculation of the active and reactive power. Then the cost function is set to a higher value, very high value. And then for the 9 possible combinations, these 3 instructions are performed. Prediction of the currents and voltages, calculation of the predicted power, active power and reactive power, and calculation of the cost function. These instructions are performed 9 times for each vector. And then from the 9 calculated cost functions, the minimal one of them is the vector which gives the minimum of the cost function is selected and applied in the next sampling period. The proposed control strategy of the slide 6 is simulated in SimPower systems of MATLAB Simulink. First, active and reactive power. You can see here that the active and reactive power follows their references without overshoot and with low ripple. And it is obvious that the active and reactive power are controlled separately. There is no effect of one on another. Here we can see the evolution of the grid currents during the injection scenarios we see. It can be seen that the currents are sinusoidal with low distortion, and the total harmonic distortion was about 2.3%. This figure shows the grid current and the voltage of phase grid current and voltage of phase A. We have made 3 zooms for this figure. First, we can see here that the current and the voltage are in phase because of the injection only of active power. In the second zoom, we can see here the lag of phase because the inverter injects both active and reactive power. In the third zoom, we have the current is lagged by half P to the voltage, as you can see here, because the inverter only delivers reactive power. This figure shows the effectiveness of the sliding mode observer. You can see that the measured and the estimated voltages are superposed. We see in this work we propose a new control strategy for grid-connected current source inverters, which offers simplicity, decoupled control of active and reactive power, and good waveforms with low harmonic distortion. Furthermore, this control technique is PLL-less. It doesn't need a phase-locked loop. The simulation results demonstrate the effectiveness and the good performance of the proposed method. Thank you for your attention.
Thank you for your Any question, please?
No question? Mr. Hamza, I want to ask a question. When you try to realize this inverter, you will face too many problems, because in MATLAB it is very easy.
Yes.
Yeah?
I am in this problem.
For example, what is your capacity of this study? Power capacity.
Excuse me?
Power.
The power?
Yeah.
Is 1 kilowatt.
1 kilowatt.
1000 watt.
1 kilowatt.
Yes.
Yeah, 1 kilowatt.
I agree with you. There is a lot of.
For example, when you remove grid connection, when you connect it to induction machine,
yes.
Did you get realize?
Do you mean experimental results?
Yeah, no experiment.
Simulations.
Simulated, yeah.
With induction machine.
Yeah.
Yes, I did some simulations of this inverter connected to a machine.
What about the result of simulation?
I get good results.
Good results.
Yes. You know, for torque and speed of the motor, the torque has very small.
You use
ripple.
field-oriented control methods or direct torque control methods when you connect it to induction machine?
I used
direct
field-oriented control.
Oh, okay.
Yes.
Okay, thank you. Now, our presentation from Poland. Yeah, Mr. Tomasz Okon. Okay, please.
Good afternoon. I'm from Poland, from Wrocław University of Technology. My subject of my paper is properties of state estimation for power system with quadrature booster in rectangular coordinates. So, nowadays, quadrature booster it's a kind of phase. It's the most basic phase shifter, and phase shifters nowadays are widely used. They are used for controlling power flows. For example, nowadays a couple of phase shifters are installed on the board with Germany, just to prevent from undesirable power flows from wind farms. It is a need to somehow it is need to apply a model of phase shifters to the state estimation. State estimation is the part of real-time modeling of power system, basing on the set of measurements and set of switch states. We built a model of topology. After that, we do observability analysis, and after that, when we can, we do state estimation. After state estimation, we can perform bad data detection. If it's not, if we don't find a bad data, we should obtain the credible image of power systems. So the purpose of investigation is to present the features of the state estimation of power system with a phase shifter. During state estimation, we minimize this following object function. When we use a normal equation method, we solve these equations to obtain grade G. We use this equation and small g. The grade G is the gain matrix. Calculation in state estimation or in power flow computation we can perform in the polar or rectangular coordinate system. In our investigation presented in this paper, we used a rectangular coordinate system. As I said, the quadrature booster is a kind of phase shifter, and it is the most basic approach of phase shifters. This phase shifter supplied series voltage, which is in quadrature, to the input voltage. So in this paper we present a new model of a phase shifter. This model can be easily adapted to different kind of phase shifters. For example, symmetrical phase shifters. But when we want to model this phase shifter as a quadrature booster, we need to add this kind of constraints. It's for here we have for rectangular coordinate system and here for polar coordinate system. Also we have this equations for which we need to introduce to state estimator. This model is very similar to the UPFC. The main difference is that in the UPFC here we had active power from this converters and from this source, and active power from this source. Some of this active power had to be zero. When we treat this model as a phase shifter, we have here complex powers. During our analysis, we considered a number of iterations, condition number of it should be a gain matrix, and accuracy of state estimation results, which was defined as a JA divided by JM, where in JM here we have ZI, here we have measurement value, here we have real values from power flows computation. And here we have estimated value and real values. This kind of analysis we can do only just for when we do some kind of a calculation. We know when we know the real value. In real life, we don't know this ZR is from. But in our investigation, we generated measurements using a power flow computation just by adding small errors represented by pseudo-random numbers. In our investigation, we used IEEE E14 bus test system with and without quadrature booster. When we considered quadrature booster, this quadrature booster was on the line between bus 5 and bus 4. We considered different series values, values of series voltage from 0.01 to 0.2.
You have 3 minutes, please. Conclude.
So, here we have results of investigation. Here we have for the lightly stressed system, and here for a higher loaded system. As we can see, when we have a power system with quadrature booster, we need more. Usually, we need more iterations in both cases. If we compare to situation when we don't have a quadrature booster. Also, accuracy is slightly lower when we need to consider quadrature booster in both cases. And here we can see that the also condition number is worsened when we have to consider quadrature booster in power system. So, the conclusion is that data redundancy level is lower for power system with quadrature booster because we need to introduce a new element in power system, and this reduced redundancy level for the power system with a quadrature booster leads to deterioration of accuracy of state estimation, increasing of number of iteration, and increasing of condition number of a gain matrix. Thank you.
Thank you for your presentation. Any question?
No, thank you. And our last presentation, Yudi Kiao from China. Okay.
Good afternoon, ladies and gentlemen. My name is Yodi Xiao, and I'm from Fuzhou University, China. The figure below is our university. It's a beautiful place. And my title is about, what I do is about the optimizing of coupled windings in wireless power transfer. And basically what we do is to use optimizing method to find a optimal group of parameters, and in the meantime, save time. And this is the main contents. First, I will do a brief introduction about the wireless power supply. And second part, I will introduce the model of the wireless power coupling windings. And then is the design method. And the fourth part is the experimental test. First, the figure below is a wireless transfer power system. The windings are transferred from the emitting winding without electrical contact to the receiving winding and then light up the bulb. And the coupled windings here, it plays a very important role in the complete system. It will affect the transmitting distance and capability and something else. And this is a model of the coupled winding. The coupled winding, it has great impact on the complete system. And now we come to the model of the CMRU. Basically, a model, it will connect or to describe precisely the electrical parameters and the performance of the CMRU, and such as the circuit model or coupled mode model. Now they can describe precisely, but we do have difficulties in describing the relationships between geometrical parameters and the electrical ones. And in some literatures, there are analytic models, and actually they can describe the relationships between these two. But when the operating frequency becomes extremely high, and so the eddy current effects become extremely high, so it's hard to describe how the magnetic field is distributed. And so that is also the reason why one analytic model is always correspond to a specific winding structure. And so most of the designers, they choose to use the simulations because they have enough or high accuracy. But basically, if the designer want to find the best optimal group of parameters, he will need to simulate all the possible group of parameters, which is very time consuming. So what we do is use the orthogonal experiment to save time and find the optimal group of parameters. And this is the model of the coupled windings. So after referring all of the impedance into the emitting winding, we can get this expression of the efficiency, which is eta 23. It denotes the efficiency between emitting winding and receiving winding. And based on this expression, we can get the maximum efficiency, which is determined only by a factor, which is KQ. And the maximum efficiency is only obtained when the equivalent load is equal to this expression. So the conclusion is the maximum efficiency is only determined by KQ. And this figure is depicted by the maximum efficiency equation. As we can see, KQ should be designed on the right side of point A if there is no limitations in the design of the winding size. And if KQ has to be designed on the left side of point A, it should be designed as large as possible to get a high efficiency. So here we introduce KQ as this design objective. And we also did an experiment to verify the model. Basically because the maximum efficiency is only determined by KQ. So it means whichever windings you use, as long as the KQ is identical, the maximum efficiency should be the same. So we just wound 3 pair of windings randomly and adjust the transmitting distance to get a same KQ, and then measure the efficiency. And we use the equivalent load, so the measured efficiency is the maximum efficiency. And this is the measured curve. As shown, the 3 curves are almost the same, especially some little difference. And I think it's the testing errors and some parasitic parameters. So it demonstrates the model. And comes to the orthogonal experiment. An orthogonal experiment consists of 3 parameters. We need to define 3 parameters first. The first is the index, which we described before, is KQ. And the factors, and because we want to optimize the winding structure, which is a PCB winding, so the factors, which is the geometrical parameters, is the winding widths and the distance between 2 adjacent windings, and the Cooper thickness T. And also the numbers of turns is also the factors. And values of factors, we call it levels, just like the number of turns. You can take 4 turns or 5 turns or 6 turns. It's also the levels. And second, we need to analyze the interactions between these factors. And the conclusion is there only exists strong interactions between numbers of turns and winding widths. This is the conclusion. And how to judge it is like in the figure C. When the winding width exceeds 3 millimeters, when the numbers of turns is 6, the KQ starts to decrease. But while the number of turns is 4, the KQ is still increasing. So we decide that there are strong interactions between numbers of turns and winding widths. And the same conclusion can be made for the receiving winding. Strong interactions between number of turns and winding widths. And now it's the orthogonal experiment design, because the Cooper thickness, according to the figures before, we can conclude that the Cooper thickness had no interaction with all of the other factors. And from the figure here, we can find that KQ increases slightly with increasing of Cooper thickness at above 2 ounces. So we just fix the Cooper thickness at 2 ounces. So the Cooper thickness is excluded from the factors. And the chart here is the level chart. Just the values of the factors. Like the winding widths, we take 3.5 millimeters and 2.5 millimeters and 3 millimeters. And this is the orthogonal chart. Because the chart is too big, so I only could use some small font. It's not very clear. But the details are here. The 1, 2, 3 to 27 is the number of experiments, which means we only need to do 27 experiments to find the optimal group of parameters. And the KQ here is the index, which is corresponding to the winding geometrical parameters in the same row. And based on the equations described before, we can use these geometrical parameters and then do simulations, and then we get the AC resistance and the mutual inductance, and then we calculate the KQ. And the last 4 rows is K1, K2, and K3 is the relative index, and the R is the range of the factors in the same column. And after we analyzing the relative index and the range, we can find, which is a very simple way. We can find the optimal group of parameters, which is as shown in the red font. So let's come to the experimental test. So in order to compare the orthogonal experiment and another commonly used optimizing way, which is the single factor analysis method, it's very simple to implement it. So we use this method to optimizing the same winding, which this is the results optimized by single factor analysis method. And we also made 2 windings, one optimized by single factor analysis, and another one optimized by orthogonal experiments, which is the method we propose, we used. It's not proposed by us, we used. And this is the winding parameters, which is measured experimentally. The KQ for the single factor analysis is 2.19, and the KQ for the orthogonal experiments is 2.46. So KQ is increased by 12%, and the corresponding maximum efficiency is increased about 4%. And here comes the conclusions. First, KQ is introduced as design objective of CMRU to make the efficiency as high as possible. And in order to improve the efficiency, KQ must be optimized as large as possible. And the design method with orthogonal experiment and FEM simulations is proposed to optimize the coupled windings, especially the air-core PCB winding, characterized with much more fringing magnetic field. Because the air-core PCB winding, you just can't decide how the magnetic field distribute. So it's hard to use the analytic model. So we should use the FEM simulation. And third, there only exists strong interactions between winding turns numbers and the trace widths, resulting in a small number of experiments. When we use orthogonal experiments, the total number of experiments is 27, but the single factor analysis, the total number of experiments is over 40, and get a less optimal results. And number 4, the proposed method not only optimize the PCB wind to get high KQ, but also reduce the numbers of experiments greatly. Thank you for listening.
Any question? No? So thanks for your great support for this session. I think it is good presentation. Thank you.
Okay.
Thank you. You can go. Our session is finished. No another presentation. Okay. Thank you.